Hi everyone, this is Avis from Automation Play. In this workshop, in this session, I'm going to cover TIA portal using S7-1200 PLC. So as you can see, I have S7-1200 1211 model and 1214 model as well, which is this one. So I'm going to be covering all that and along with my trainer board built by Mindstrong Engineering. So we are going to cover all that. We are going to cover basics from TIA portal right from scratch. We are going to compare different Siemens PLC series, and we are going to cover ladder logic part as well in TIA portal, and we are going to solve some applications, carry out some applications on factory IO as well. So it covers all the basics, it covers some applications as well, it would cover diagnostics as well, and it would cover the hardware PLC as well, so that you can work around this beautiful PLC. I believe TIA portal is the best software to learn PLC. It also offers 21 days trial version which you can use. Siemens also offers an excellent starter kit which you can get from different websites as well. I will share the links for that as well. So ultimately this workshop would provide you the basics on TIA portal and S7-1200 PLC, and after that, if you wish, you can enroll in my full specialization available on Siemens or individual TIA portal course as well, or S7-300 or SCADA or advanced hardware and communication, and some exciting stuff as well available at automationplay.com. Apart from that, Siemens is the biggest automation organization in the world based in Germany, and its PLCs are used globally. I have provided trainings in 100 plus countries to thousands of students and to bigger Fortune 500 companies as well, to world top 10 companies as well, available in top 10 companies. So this product here and TIA portal is running plants globally, right? So let's dive in. So even if you don't have physical PLC, you don't have to worry at all. I will provide you the 21 days trial version download links in the video description. You can download, you can watch my step-by-step video on installing and activating this amazing software, right? You can turn your laptops and computer into full automation servers, you can say, where you can program PLC, HMI, SCADA, and solve real-world applications using factory IO, right? So let's dive in. In today's lecture, we are going to discuss programmable logic controllers. We are going to cover the basics of PLCs, and later on we will mainly discuss Siemens PLC series as well. So let's begin. Here there are some basics of PLC. Programmable logic controller is an industrial grade computer used for automation of machinery and processes in an industry. So it works by accepting signals from inputs that are different conditions that comes from the sensors, and energizes the outputs based on the logic programmed. So it is us engineers that program the logic into it, the controller. Here are my inputs, here my outputs, and the logic is programmed into the CPU. And we use this PLC system to automate certain processes. So it offers higher reliability, more flexibility. It is cost effective when it comes to complex systems, because if you are going to operate few motors, you can even use relays and contactors as well, right? But it is used cost effective for controlling complex system, easier programming and troubleshooting because it is programming based. So you can use software, you can use HMI to troubleshoot by using alarm handling. Faster response time, it works in microsecond, millisecond. Immune to electrical noise and resistance to vibration, so it is industrial grade controller. How PLC functions, or how PLC control loop works is, it read inputs, scan the program against the given conditions, it operates output as per logic, and it continues that cycle in milliseconds. So PLC can be divided into three parts as we saw earlier: CPU, input outputs, and programming device. Here's a short example of PLC operation. I'm using wait a second, I can't find my cursor. Okay, that one is better. So this is my conveyor. This is my box. Here's my motor that operates this conveyor, and here's my sensor. So what's happening is box is being transported till it reaches a sensor. So box starts from here, goes to the sensor. Motor is running the conveyor. When the boxes reach the sensor the sensor sends a signal to relay or PLC, thus stopping the motor. So that is our common application in industry. We will have simple or complex processes as well. We have to identify inputs, we have to identify outputs, and we have to understand the process to automate it. This is the overview or block diagram of PLC. It has power supply, it has CPU, user memory to store user data, data memory to store data that is being generated from the program, serial port as well, so that I can use that to program my PLC. But the S7-1200 PLCs or 1500 of Siemens PLCs have now Ethernet port, so we are going to use that. It has input module, have optical isolation, and same for output module as well. So there are different applications. One application is single task, where single process being controlled by single PLC. This is for standalone application. In multitask, multiple processes being controlled by a single PLC, but it has many IOs or external modules. In control management, there's master PLC controlling multiple slave PLCs for complex processes. Programmable logic controller can use these 5 programming languages as per 61131 standard. So functional block diagram, which is graphical but mostly used for process flow, ladder logic graphical, which is used for electrical flow, structured text similar to Pascal, or it can be called a high level language like C, C++. It is textual, used for calculative purposes. Instruction list similar to assembly, this is textual, boolean. And SFC, sequential function chart, which is graphical for sequential processes. So the most popular among that is ladder, then comes FPD, then comes ST as well. Ladder or FPD is comparatively similar if you don't have programming experience, but ST is high level language, so you need some good basic understanding of that as well. So moving forward, here's just a short example of ladder logic. We have inputs or contacts on the left and outputs or coils on the right. These are two power rails which makes the shape of a ladder. PLC hardware consists of different parts. So for example, here are some inputs. These are going into input signal module. So here, this is an example of Siemens. So Siemens can have onboard IOs as well, but if you need more IOs or more input output, you can use signal modules. So, and then here's the main CPU, which has been interfaced with HMI, human machine interface, that can use to visualize or control parameters. Here is our output control module, which sends signal to output actuators such as motor. So this is my CPU. It has indications as well. It has Ethernet programming port as well, onboard IOs, and here my signal modules, which have module status LED, input channel LEDs, output channel status LEDs. So in case of failure, the module will let us know by module status LEDs. The signal module comes in both discrete and analog, and then there are special purpose modules as well, such as temperature, load cell, and so on. Communication modules. So S7-1200 CPUs use Profibus modules. S7-1200, since they have built-in Profinet ports, Ethernet ports. So as you can see over here, they can easily be integrated using that port, using that Profinet. Otherwise, there are separate communication modules available as well, like for Profibus, for Profinet. As we discussed special purpose module, in that case, here's an example of closed loop system that is mostly used using PID control. Programming concepts are being discussed over here, like Siemens addresses works, absolute addresses work with percentage sign I0.0, I0.1 for two inputs and one output Q0.1. And here in FPD you can see direct AND block is being taken over here, which works in a way that if both logic input are high, then output would be high, and then here's an assignment function which turns my output on. PLC can be compact, slim, or can be modular, fixed on chassis as well. We can use these for standalone or small mid-range applications. We use this for mid-range to large control system applications. I/O can be both digital input and outputs. There can be analog inputs and outputs. Digital work on 0 to 220, 0 to 24 volt. Analogs signals work on 0 to 10 volt or 4 to 20 milliamps, that are mostly popular signals. These are some common inputs like push button, stop push button, emergency stop button, selector switch, sensors including limit switches, proximity, ultrasonic, and output include lamps, motor, valves. So selection, as we briefly discussed, we must know how many input outputs are in our machine, nature of input output like digital or analog, or if digital NPN or PNP, then any special requirement like temperature, load, size of control program, whether it's a small machine, it's a big machine, data collecting requirements, future expansion. So you can select a PLC that can have additional IO modules or that can have some spares points. Any case, Siemens offers such a great tool that you can use TIA selection tool to see what modules or what controllers, what IO modules would you need for a process by using this tool. Here are the Siemens PLC series that we are going to discuss. This is S7-1200 that are mostly obsolete now. It is a compact PLC with onboard input and output. It is micro PLC for lower performance range. Software name is Microwell. Cable interface is PPI Profibus that works on serial protocol of RS485. Then comes the S7-300. It has been one of the most popular and legacy systems for Siemens that have that are now mostly obsolete as well, most of the models. So it is a compact. It can be compact with onboard IO or it can be modular as well. It is for medium and low end performance range. Software is Step 7 Schematic Manager. Cable interface is MPI, which is multi-point interface, and Profibus. S7-400. So this controller is quite popular for process automation applications used in complete DCS applications with PCS7 software package, and it is for high performance and medium range. It is a modular PLC. Interfaces include MPI TP, Profibus TP. Okay, S7-1200 that we are going to use in this course, it is for medium and low end performance range. It is compact PLC with onboard IOs, can have additional modules as well. It uses the one of the most popular PLC programming software in the world right now, that is TIA Portal, Total Integrated Automation. Cable is Ethernet, interface is Profinet, high end, medium and performance. It is being repeated over here. It is for medium and low end performance range. So I have to correct that, and it uses Profinet obviously. S7-1500 is advanced and modular controller. So difference between both is S7-1500 is primarily designed for control applications, process control or control applications, or large control systems that have large number of IOs and large number of analog and PID loops. So it offers highest system performance, as Siemens says. It uses TIA Portal software. Cable interface include Ethernet or Profinet. Then comes our ET200 with integrated CPU. So it is a distributed IO system that is used to install in remote areas within the plant or remote locations within on the shop floor. It can be it is offered with or without CPU. Without CPU means just IO modules and that are receiving information and sending that information to main PLC. High and medium and performance software is CI portal. Again, cable interface is Ethernet and Profinet. So these are some slides that I'm going to share with you, which you can read in detail about S7-1200 PLC, 1200 PLCs, 1500 PLCs, and ET200 distributed IO systems. So just a small comparison, it has onboard IOs, the S7-1200, S7-1500 completely modular. So CPU is separate and input signal module and output signal modules are offered separately as well. It has some compact version as well. If S7-1500C is written over here, that means it has some onboard IOs. This is just a deeper look of S7-300 PLC. It has a status indicator and a stop switch. Article number is mentioned over here as the same CPU as, for example, this is S7-300. It can have multiple article number with different specs. Digital inputs on the top, digital outputs on the bottom over here. This is my S7-1200. It has, you can see, 6 inputs, 4 outputs, and every SM1200 PLC have 2 analog input on board. If I need an analog output, I can connect a simple signal board over here, or I can use a signal module as well. It has a Ethernet port at the bottom, which you can't see at right now in the picture, but I'll show you in the hardware section, and it has multiple status indicators as well. So again, some theoretical slides which you can read. How we set up PLC is we used to have MPI cable to program 300 and software is Semantic Manager software, but mainly we are going to use Siemens PLC as obviously 100% of the time we are going to use S7-1200 PLC. It uses IP addressing to communicate with my programming software or with other devices as well. So this is the overview of software. I'm going to use version 15 now. There's a latest version 16 as well, but since to keep it simple, and currently I have installed this software, so I'm going to use TI Portal version 15. So most of you wouldn't have hardware, so I am going to use PLC SIM as well to simulate the programs, and you can use that as well. I will show you how to download this software as well. Communication methods. So there are different communication methods that in general PLC uses, or in if you talk about Siemens as well, Siemens have these popular communication methods as well. Communication is obviously used to interact with different devices, communicate with different devices among each other. Serial communication is or used to be the most popular protocols. It is RS-232, 422, 485. So even Siemens 200, 300 protocols such as MPI, PPI, or even Profibus uses RS-485 interface. Industrial networks, so such as we are using Profinet in S7-1200. It is a purely network based or Ethernet based interface. So it uses industrial Ethernet RJ45 connectors as well. Yep. Okay, here's an interesting thing. Two types of cables used for industrial Ethernet, including Profinet, are shielded twisted paired cable and fiber optic cable. So normally you would see these cable in your home as well, but we use fiber optic as well in industry to use in application with high level of electrical noise. Profibus DP, as you can see, this is the board of Profibus DP. This is the connector. There are two types, DP and PA. DP is for factory automation, which is mostly discrete control. PA for process automation, which includes for example, an oil and gas industry is a good example of process where we are using DCS system as well, such as S7-400. So Profibus is a master slave system, and it offers a speed of 12 Mbps. Okay, this is the most popular communication network for factory automation or for motion control. As you can see, there are three different methods described here, from 100 millisecond to less than 1 millisecond. So it is isochronous real-time communication, which is the fastest Profinet offers. Profinet allows field devices from many suppliers to be easily connected to the network. As it obviously works on TCP/IP protocol, it is quite easy. Profinet also protects investment in existing network by simplifying their integration. Okay, there are some things that you can read yourself. Profinet device types, it can everything. I mean, Siemens offers, whether it's HMI, PLC, distributed IO system, like that, everything can be connected easily using Profinet. Okay, again, there are some things over here which you can read. Industrial Ethernet uses industrial switches to provide the performance and reliability needed for high-speed factory networks. So it can offer up to 100 Mbps with full duplex operation. That means multiple devices can talk to each other at the same time. Scalance Ethernet switches are widely used in an industry. Wireless communication is becoming popular as well. WLAN as mentioned here, and in few years we are going to use a trend of wireless communication. Obviously, Siemens offer these modules as well that works on. There are modules that works on Wi-Fi. There are modules that work on radio frequency. ASI is a popular communication method. What happens in ASI, it replaces the complex wiring, and it offers a master communication with up to 62 slaves. So how it works is, it uses as you can see this yellow cable. What it does is it provides power to these modules, and it can be used to generate signal as well. So our power and our signal travels through the same bus. So what it does is it reduces the cost of wiring, it increases the speed of communication as well. So with only two wires which can transfer both data and power. So imagine if you are using 4 core cables in the industry, that can be used to only two wires, limited to only 2 wires, that can save a lot of cost and time. Another example is an IO link system. It's a point-to-point system, not a field bus. It uses a 3-wire cable, power supply, and an IO link master. Up to 16 devices per master are allowed. The accompanying graphic shows 2 examples of IO link masters. So as I'm going to use in level 2 or 3 courses these IO link devices as well. So these are quite popular. These are installed in the field, but it is not called field bus. It is actually a point-to-point system, which we are going to discuss later on. We are going to discuss the PLC programming, especially in Siemens. So this is my software, TIA Portal, Total Integrated Option. You can create new project, write PLC program. We cover these different softwares or different versions. Since we are going to use S7-1200, we are going to use TI Step 7 Professional, so we can work both on PLC HMI, and in later courses we will work on SCADA as well. TI Portal is a configuration programming of S7-1200 PLC. Supports IEC 61131. It supports ladder, FPD, structure test, or structured control language, and 2 of the other languages, instruction list and sequential function chart, can be used in S7-1500 PLCs. So it says S7-400 PLC were developed prior to the introduction of TI Portal software. A version of Step 7 Professional separate from TIA Portal is also available for use with these PLCs. So they have offered a version that can be used with above older PLCs. But there are some variants of S7-400 PLC as well that can be programmed directly from TIA Portal Professional. So it includes S7 PLC SIM software as well, which can be used to simulate our programs. Best thing that Siemens offers is it offers a complete modular programming structure, which is quite good when you are programming complex tasks. So normally we have linear program, a single program created in the same network. In Siemens, we can create different multiple programming blocks, and interesting part is that each programming block can be in a different language. Like if you are doing some calculations, you can use SCL. If you are making some process flow, you can use FBD, things like that. And main program can be in ladder language. These are the program blocks. We use organization block to that has our main OB, or we can use some cycling interrupt as well when we program our PID. We use function blocks that can again help us in creating multiple blocks, sub blocks like that or subroutines for each machine. For example, there are multiple machines. I can create different blocks for each machine. Difference between function block and function is function block stores the data, like timers and counters can be used over here, and function does not store any data, like bit logic instruction can be used over here. And data block is can be used, you can create a separate data block to for example, you are automating a tank. You can create a data block for the calling the tags of that tank, or if you are creating a function block, it automatically generates the data block as well. CPU memory obviously can be used. It has CPUs have separate memory card as well to store our program backup in case our program is erased in the main PLC. It can call program from our memory card. Here are some instructions. These are ladder. It precedes by the percentage sign, and I means input image, Q means output image, 2 means second byte, and 4 means fourth bit of second byte, and it is separated by a dot. We will discuss it later on. There can be multiple data types: integer, double integer, real. We are going to discuss that as well. And yep, these are some slides which we are going to discuss later on when we practice this. Thank you. Hi everyone, this is Aviz from Automation Play. In this lesson, I'm going to discuss about PLC data types, memory, numbers, and code system. So I'm going to give a very brief overview, right? Memory types, memory storages comes in these different sizes. Modern PLC use modules that have solid state memory. Most of you already know that. We donate memory, indicate memory size in kilo as per K, mega as M, and giga as G, right? So one byte of sorry, 1 byte of data is equal to 8 consecutive bits. Each bit is either 1 or 0. So if we are using a Boolean logic, for example, using a 1 switch that is connected to PLC, that would store 1 bit of data. It should be either 1 or 0, right? Similarly, if there are 8 bits, that would be 1 byte. If there are 1024 bytes, that would be 1 kilobyte. Just remember that 1 kilo is not 1000, it is 1024. And similarly, if we have 1 megabyte, that would be when we have 6 zeros around, right? I believe that would be, let me show you, 10 tens to the power 6. That would be 6 after 1, right? That would be your 1 megabyte. So that's 10 to the power 6. Then 1 gigabyte, that is 10 to the power 9 bytes. So it is not something that we have to work on, because if we process discrete data, analog data, that is being stored in the memory, right? It's not our job to how it is getting stored, but for some knowledge, just to get some background, we must know how it works. Second part is we have 4 different memories: non-volatile storage, where user program is stored, right? Located on a memory card or in the CPU. So most oftenly we use CPU internal memory to store our program, or we use memory card inside PLC as well, that once if the program gets erased for some reason, it picks that program from the memory card. Non-volatile means it is permanent storage. Volatile means that it is temporary for some elements of the user program that is stored at that time, just like our RAM in our laptop or computer. Load memory is non-volatile storage for a limited amount of work memory. And then global memory, GIQ, process, image tables, and bit memory. So when we process input and output addresses or memory bits, it is stored in global memory. Global means that can be used by all other places inside the PLC. Okay, so this one is PLC connects to wide variety. Yeah, so it just shows we have connected a push button that is connected to power supply. It shows it's getting on and off. Since CPU is just a processor, a transistor based processor, it processes logic in 0 or 1, high or low. It's a machine level language, right? So it just shows all the conversion is being done inside the PLC, and consecutive binary bits are also grouped in length. Yep, so that's what's happening. So it's push button off, it detects off, my logic is 0. It detects on, my logic is 1. Even if we are processing 0 to 10 volt data, it converts into 0 and 1. Okay, so now comes number system. Depending upon the brand of PLC can either be using decimal number system. That means that can be input 0, 1, 2, 3, 0 to 8, 9, 6, 7, 8, 9. Or it can be on octals, that is 0 to 7. It has a base 8, right? So that varies PLC to PLC which number system it is being used over there. I won't go into the number system because that is not part of the course, but just remember that decimal numbers are 0 to 9 with base 10. It's been shown over here as well. 1, 10, 100, 1000, 10,000. Its calculation is being done over here. So there are different kinds of conversions we do in number systems, right? Then there are binary. Binary is basically 0 and 1, which is works with our processor, right? It just detects Boolean or binary language. So it has a base 2, and it is either 0 or 1. Yeah. Then octal. Octal has a base 8, and it goes from 0, 1, 2, 3, 4, 5, 6, 7, 8, like that. So why do we use number system is because whatever information we are getting from our sensors or devices, it's been converted, right? So it depends that conversion is depend upon these number system. Then we have hexadecimal 0 to 9, then comes some alphabet, and it has a base 16, right? So sometimes we are using in programming hexadecimal or decimal system as well. Octal we have already discussed it. Then there's binary coded decimal. That means it's decimal but binary coded, like it is 0, 1, 2. This comes as 1, 2, 4, 8, right? So 1, 2, this one is high, so 2, 1, 2, 1 plus 2, 3, 1, 2, 4, 8, this is 4, like that. Now comes the main part, data type, that I wanted to discuss. Data types, we have Boolean, short form bool. This is 1 bit. It comes in 300, 1200, 1500. We have byte. Byte means 8 bits. That means it comes in all these PLCs. 1 byte is 8 bits, as we discussed earlier. 1 word is 16 bits. Double word is 32 bits. Long word is 64 bits. So this is how it works, right? 1 bit would store either 0 or 1. 1 is state of data. This means 8 bit. How much data would that store? Let's see that. 2 to the power 8. 256. That means I can store 0 to 255 numbers. If I am adding 200 plus 10, over here it would show in the byte of data. But if I am adding 200 plus 100, that would be 300. Then I have to use word data. How much word can I store? 2 to the power 16. This much of value. And if we are storing negative values for that, that means it would be 32,000 something and 32,000 something, minus 32,002 plus 32,000, around that. Then we have double word and long word. So it is dependent upon, this is dependent upon the accuracy or resolution we needed. Higher the bits, obviously, uh, good, higher the resolution of the data. I mean, you can process large amount of data, right? Then we have integers. So short integer 8 bits, unsigned 16 bits, unsigned double integer 32 bits, unsigned long 64 bits, signed short one are positive, and these one can be used for both positive and negative values. Signed short 8 bits, signed 16 bits, double integer, long integer. And for S7-1200 we have only signed integer and double integer, and in S7-1200 we have most of these, and in 1500 we have all of these. Real number, that means a floating point number, 1.001, 1.065, whatever it is. So we can use that. Real number is, data type is real in all these PLCs. It is by default 32-bit, because if we are taking decimal point, that means there's a large amount of data. And then we have long real numbers that are 64 bits. It's not in that, it is only available in these PLCs. One thing to notice is that sometimes we are using word as well, or we can use integer as well for the numeric calculations, right? So do remember that. But for integers mostly, for numerical calculations, we are mostly using integer or real numbers. Yeah. It is the same table. Okay, it shows calculation as well. Boolean, false or true, 0 or 1. For octal, 0 or 1. 16 has 0 or 1. So here shows a data type that we discussed earlier, that how it is used. If PLC is designed in octal or hexadecimal, it can process information like that. Address I1.0, I means input image. 1, that is byte, and 0, it's bit address. This is byte, this is bit, we will discuss later on. Q, output image, and this is memory bit. Then this is our data block, we can use that as well. Yeah, then we have byte, IB, MB. Make sure you are using capital sign for that. Byte unsigned integer means 0 to 255. Yeah, unsigned, that whole values are positive. Word, okay, word, as we discussed, we can use this amount of binary, 16 bits of data, right? 16 bit. Or we can use unsigned integer 0 to 65535, octal as well, and hexadecimal, FFF. MW10, that is memory word address. Or we can use IW or QW as well, like over here, ID double word, IW word, IB byte, or MD memory addresses. And we use IW when we are taking data from PLC, analog data from PLC. We use memory addresses for moving values or for calculations, right? Then we have double word. Over here you can see unsigned integer, octal, all these values. So you can see very large range. It is used when you are processing large amount of data. For example, your plant have a production in millions, right? So we can use that to calculate overall production, right? Here it defines further. One more thing is, it shows word or double word, while shows integer in their number type. So data type is word, double word, but we can use integer data type as well. So there's not much of a difference in that. Yep, it shows table. I further included that table just to show you, to remember all these data types. Real numbers, you can see after a decimal point there are certain range, as you can see that now depending upon the resolution you can use these, it is in 32-bit format. Now here comes one more interesting part, data types and mapping. So when we are using data types are used to specify both the size of a data element as well as how the data are to be interpreted. Yeah. So it defines size as well of a data element, length of a data element, and as well as how data are to be interpreted. For example, it's integer data or boolean data, right? Now, this what it defines is, in this example, memory area and byte address M. M is our over here bit memory area, and 3 equals to byte 3. That means this is our block, right? This is 0, 1, 2, 3, 4, 5. So for example, we have this 0, 1, 2, 3, 4, 5, F and E. So here shows bits of the selected byte. These are bits and these are bytes. So we have 5 bytes of data, 0, 1, 2, 3, 4, 5. So we are using byte 3 over here, 3 byte, and it's 4 bit. So M 3.4. That means if I'm using M 3.4 that is taking some boolean value, it would be stored like that in some buffer, in some memory area, right? So this is what is being shown over here. If I'm using I 0.0, that would sorry come over here. I 1.0, that would come over here. I 2.0 come over here. I 2.7 would come probably over here. Yeah. So this is how data is being used. If I'm using MW, right? MW1. MW1 would be 1 byte of data. So that means this whole block would be used by that, because it's an analog data, some kind of values is coming. So it wouldn't just use one single block. So this is how data types, and mapping is done in Siemens PLCs. And one more thing, it is preceded by a percentage sign. It's written over here, preceded by a percentage character or constant data to be used by the instruction example. So do remember that. And it is separated by 3, M3 by period dot, and to separate bit addresses like that. So that's all for this lesson. Thank you. In this session, we are going to create a new project in TIA portal. Let me start it. I'm going to run this as administrator so that it does not ask for license again. As sometimes if I open it normally, it does not detect the license. So I'm using Windows 10. I have a Core i5 laptop which is 7th generation. So this is still a powerful software which will take its time. So it is an overview over here. I mean, there are different options available. By using online and diagnostic option, you can directly detect your CPU over here in accessible devices. But it is useful when you just want to detect your PLC, check if its communication is working or not. So you can use this function at that time. So as it says diagnostic, so instead of creating new project and going to new program, you can just directly detect it from over here. It is taking such a long time. Okay, so here the interface is Profinet interface, which is set in my control panel, PGPC interface. And here's my you can say LAN card, by which I will plug my Ethernet cable connected to my PLC. Right now nothing is plugged. We are getting an overview of TIA portal. So I'm just going to get to start. Here are some recent projects that I have created, which are being shown over here. I can create new project from over here. I can migrate a project. For example, you have a project of TIA portal, earlier version of TIA portal. So you can select a project from over here, source path, and you can set a target path over here, and it will convert earlier versions project to this TIA portal version 15 project, and you can easily open it then. Here it says installed software. As you can see, version 15 is installed. Interface language can be changed from over here. You can use help function, which will have all the programming and hardware, you can say hardware help, which you can access in case of any confusion. So help function and programming manual or Siemens PLC manual are, I believe, two best references to be used. So here I'll name my new project demo in English. I'll click on create. So there are multiple options over here as well. If I have to open the existing project, I will click over here. But right now, I have to configure a device. If I have to directly write a PLC program, I'll choose this option. If I have to use, for example, PID block, I can use this. I can configure a HMI screen from over here. But we are starting a project. We will use creating new device. I'll click over here, add new device. So from here you can add PLCs, HMI, and PC based HMI or SCADA systems. So right now I'm going to go over here. I will go to S7-1200 CPU, and my physical PLC that I have, it is 1211C version. For simulation or for TIA portal purpose, education purpose, I can use 1214 over here. So let me explain this. Over here it says CPU 1211. It's the version of different S7-1200 PLC. As you can see with time, there are multiple variants. C means compact, and compact means that there are certain number of inputs or outputs on board. Like if I select the PLC, you would see over here that there are certain number of input and output. It is written over here as well that 14 digital input and 20 are of 24 volt DC and 10 digital outputs. Further, AC, DC, RLY. AC means AC power input power, and DC means DC input power. Here DC means inputs, number of inputs, like for example I'm using push button or sensor, that must be of DC input. And here this is output rating. So here in this PLC I have relay outputs. Here in this PLC I have DC output. So DC output I can only use 24 volt, and for relay output I can use 24 volt, 110 volt, 220 volt, right? And if I open a PLC, there are 3 different variants over there as well, with different firmware version, and with these are article numbers. So there can be, for example, here it says 0.1 millisecond per thousand instruction. Here it says 0.04 millisecond. So there can be differences in certain features or speed of the PLC, right? And here are the firmware version. So for S7-1200 simulation in TIA portal version 15, I am going to use version 4 or above. If you select an older version, it wouldn't be able to simulate. And when we program a physical PLC, we have to match the version of this physical CPU and the version that we select over here. If you don't know the version, select the lowest one. Article number would be written on the PLC, but like over here there can be different version, right? So select the lower version so that you are able to program if you don't know the firmware version. There are certain features written over here. I'm just going to add this device. So this is my CPU, as you can see over here. Here I can add communication modules to the left, and here I can add IO modules to the right. So modules are written over here, which we will see it later on. For configuration, CPU configuration, I can just click over here on device configuration. Let me try again. Okay, let me press use Alt plus enter. I believe I have to drag that window from the bottom. It happens every time. Okay, so here are the configuration. I can use zoom button as well. As you can see, I can further zoom in. Okay, that is too much. I just want to show you how good this software is, right? So you can see the status LEDs over here. You can see the inputs and outputs, and it addresses as well. Like, we can assign tags directly as well, which I will show you later on. So that's better. So I did not click it earlier. So it is showing the detailed information over here. Yep. And here are the IO tags, right? So these are the, since every S7-1200 PLC has two built-in analog inputs, these are being shown over here with data type integer. And here these are boolean inputs. I can assign a name over here as well, like input, and here you can see. So these are absolute addresses, and these are symbolic addresses that are in human language. So by using this, we a property window, we are configuring our PLC. We have further online and diagnostic option as well. From here you can go online, or you can use this button as well. You have diagnostic status, that diagnostic buffer. It shows all the system events alarms over here. It is CPU cycle time, memory profinet interface. Again, you can set IP from over the here as well. So what we can do is, we just, one more thing, here is the main program block, from where you can enter your program. Either you can select ladder logic, FPD, right? And here are on the right, these are all the ladder logic functions. I can change this language to FD as well, and you can see it would show the FPD editor now. So on the left, it is a project tree, which we'll mostly using adding new devices, device configuration, main OB block. Here we will work on PID blocks, external source files, PLC tags that we can assign from over here. Data types can be made, watch and force table for monitoring or troubleshooting purposes, device backups, traces, uh, for displaying information, program info. Okay, local modules that shows external modules over here. So this is my project tree. This is my detail view. If I choose a function over here, I can see its detail over here. On the right, I have basic instructions, or if I go to devices and networks window, it shows all the drives or PC systems or HMI or any other device that I can add from over here, right? And if I click the main OB, in which most of our program will be called or written, it would show the timers, counters, and all the functions over here. It would show PID or motion control functions. It would show distributed IO, data and time of day, and some other special functions over here. Testing, if I go online or use simulation, my CPU would be status would be shown over here. I can search different parameters tags from over here. I can add for some libraries, special libraries as well. Over here you can see go online. Here's the upload button, download button, and accessible devices as well, that which devices are currently online. And from down bottom are the properties window and info, which would show compile errors if there's any, and diagnostic window as well. So this is the complete overview. If I click just simulate, because PLC right now is not connected. So instead of my Ethernet card, it shows over here PLC SIM, because I'm using a virtual PLC. And it's taking time, but it is going to show my PLC over here, right? So I can click on load. Also, I haven't written any program, but I'm showing you what happens if we compile and upload a program. It is right now compiling. I'm going to click on load and finish. So it's not on run mode right now. I'm going to click on run, and it is going to blink back and forth, and it is stable now. Let me click on the monitoring part. Now as you can see on the left and on the right, it is showing my PLC status, and over here everything is green. That means there are no errors, there are no warnings, everything seems perfect, even though I haven't written a program, but it shows like that. So that is how we take our PLC online on simulation. Here I can use upload and download button as well. So in the next lesson we are going to discuss tags. So let's discuss PLC tags. This is my default tag table, right? If you remember, I went into device configuration, and in the properties window, Alt press enter. One more thing, here it is showing green as well. That means our PLC is online. IO tags. So I created tag from here as well. Tag means, since we are using these you can say absolute addresses, which points to these terminals where my inputs or outputs will be connected, we use symbolic addresses such as input, output, sensor 1, sensor 2 to make it seem better, make our program structure better, and to make it easier to understand, right? So before creating our program, we normally create PLC tags beforehand. Like I have for example push button, so it automatically addresses i0.01 i0.1. Let me delete this tag and call it i0.0, and take one more tag. This is output, so I'm going to use Q 0.0. So what I'm discussing is this. I have opened a PPT as well. Here's my absolute address, which is logical address. Here's my limit switch, which is symbolic address. And first 0 means this is 0 byte. So PLC inputs or outputs are divided into bytes and bits. So addresses, I means input image, 0 represents byte 0, and another 0 after the dot, which is a period separating bit address. This 0 indicates bit I0.0. So afterwards I0.1, so 0 byte and 1 bit, 2 bit, 3 bit, and so on. So 1 byte have 8 bits of addresses, and percentage sign is used to indicate that it is an absolute address. Step 7 automatically uses it. So if I take I1 over here, I1 means first byte, and again first byte will have 7 bits, second byte, third byte, and so on. Same goes for Q0.0, that are used for output image. Yeah. So tags, we were talking about tags and addresses, right? So I've used tag over here. Here you can see, if I click on default tag table, here this is showing me certain details view as well. So what I can do right now is, also I can make these windows floating as well. For example, like this. So now if I go to main OB, oh wait a second, if I go to main OB and let me convert it to ladder, since we are going to start from there. Okay, I've got to take it offline. Ladder, great. So I can use input and output like that. Now if I use this button right here, it shows my tags. As I explained earlier, in ladder we take inputs to the left, outputs to the right. So just by using that, I am calling tags from over here, which I have already signed. One more thing, what you can do is that you can create tags from over here as well, like push button to PB2. I have written over here. I go to right click, define tag, and PB2. Okay, there are 4 things over here. Local temp means the tag that is going to work in the local block, in this block only. So it can be used for intermittent logic or interlocking within the program. Global memory bits like M0, MW, the MW bits addresses are used for storing data. M0 bits can be used within the program, within the memory. These are internal bits and are used with HMI as well. Global input and global output that we are mostly going to use. Global input means that are my physical addresses, I0, I1, and global outputs means Q0.0, Q0.1. So I'm going to use global input over here. It automatically assigns the next address because I0.0 was already assigned, and PLC tag table. So it is going to put into tag table, default tag table, I0.1. See, and now the tag is shown over here as well. And I can create another output, lamp underscore 2. Let me give it Q0.2, and percentage is automatically assigned. Not Q0.2 because I haven't taken Q0.1. Okay, that seems better. I take another coil and yep, I can drag my tag from there to here as well, which is really cool. Furthermore, you can create more tag tables as well. Like if I have multiple machine, I can create, for example, I can call this tag table tank 1. So you can create multiple tag tables as well if you have a modular structure or modular program. So there are different ways to create tags over here, and meanwhile you can use user constant as well, like timer underscore value. I'm going to give it name and teacher and going to value 10. Now what happens is So what we use is we use 10 value constant like that and we move it to MW20. For example, it's our register which stores data. Now instead of using values like that, and if there's a same value that I'm going to use in other blocks as well with other functions, instead of using and typing these values, what I can use is, as I use in default tag table. By the way, all my windows can be selected from over here instead of using the project tree. So I've created a 20 value over here. I named it timer value user constant, so I can call it over here directly, right? So this can be used in different places in the program. Normally we are not using this as much as the tags, but still it's quite useful to know. So these are the tags. If I'm missing anything, it's a long course, so we will be covering everything hopefully. Yeah. So in last exercise we use tags. Now I'm going to discuss further a little bit about the structure of the program. Here, as you can see, we are working on main OB. If we are going to use main OB, we can create different networks like that. Like there's a first push button network. Okay, here's a mistake. It is using, I'm going to use lamp output, right? Okay, so yeah, in this network I'm operating first push button. In this section I'm operating second push button and lamp. So for example, you have 10 motors, you can create separate network for all the motors. So this is how network helps you to organize a program in a much better way. What's another cool thing is that you can create different functions block as well. Like here's the main organization OB. We are using OB1. Okay, your OB1 you can't delete it. You have to use this by default. It's in every program. Even if I'm creating different functions, I have to call them in there as well. Now if I'm using there are some interesting organization blocks as well. Like mostly we are using cycling interrupt for our PID function, right? Few of others as well we are going to see later in the course, but mostly we are going to use cycling interrupt. Here there are two different things, function block and function. If I'm creating a function block, for example, if I'm using timers or counters or move instructions, if I'm storing certain parameters, if I'm storing certain data, I'm going to use function block. And here you can see three different programming languages because only these three are available in S7-1200. If I'm going to use S7-1500, I can use instruction list or S7 graph language as well. If I'm going to use a function, what happens is I can use my bit logic instructions over there because it wouldn't allow me to store any data. It wouldn't create any data block. So for bit logic instructions where I'm not storing any data, I can use function. For functions where I have to store some data, I can use function block, and I can create a global data block as well. For example, I'm using automating different water tanks. I can create a data block and use its parameters in that. It can be a little confusing right now, but we are going to check later on. For example, I'm creating one function block in FPD language. I have clicked OK. So as you can see, FP1 has been created, and I can create function over here as well. So now as you can see, function is created in green icon, function block is in blue icon, it's in ladder, and it's in FPD, which is quite interesting. For example, I'm using an AND gate over here. I can put some addresses. Let's give this a same address. Not that. For example, I'm putting I0.0 over here, I0.1 over here. It's an AND gate, right? And I'm taking one assignment. If the both input are high, then my output will be operated. So this is my normally AND gate. And here, for example, I0.0, Q0.0. Right now I'm taking the same addresses in both blocks, but we use, for example, there are different machines. We can create separate function blocks or functions for those machines, and within those blocks we can create separate network for different routines in those machines. And how it is going to happen is I can now call that functions block into the main OB like that. See over here. Now it is asking to create a data block because it's a function block. It would store some kind of data. So like that, I have a modular programming structure. What happens is PLC scans the first network, second network, third network, and fourth network. It would jump to my FC1 program. Then it scans further, comes back, and it would jump to my FV block. Then it comes further and to the main block again. So that is how modular programming works. That is how you can organize your program within TIA portal and give it such a cool structure in this. So in this lesson we have already created a program. What we are going to use is we are going to perform a simulation. Let me delete those functions that we had earlier created. So in this lesson we have already created a program. What we are going to use is we are going to perform a simulation. Let me delete those functions that we had earlier created. Okay, cool. So we are in main OB. Come on. Here's the compile function. Normally when we take online or download, it automatically compile the program. There are 0 errors, 0 warning. Here's my PLC SIM that has already been opened since our first exercise of CPU configuration. So what I can do now is, if you don't have this PLC SIM open, you can just click on start simulation. Otherwise, what I can do directly is, okay, let me just show you again. You have created this program. For example, there are two network over here. I'm just going to click on simulation. I'm going to click on start search. I'm going to load the program. I'm going to click on run and click on the classes over here to monitor my logic. Let me put this over here. So as you can see, it is now operating. Now what happens is, because these are physical buttons and my PLC is not connected, I cannot modify it from over here. what I have to use is I have to click on extended view so that I can modify the status of these bits. So I have to create a new project as well. This is basically a PLC SIM software. Now I have opened an extended view of this software. It is creating a project in my PLC SIM as well. So this is my PLC SIM. I'm going to click on device configuration so that it picks up my configuration from over here. You can do quite much with PLC SIM if you don't have hardware, and in case you wish to test program before downloading it on your machine, you can obviously test it using PLC SIM. So it shows the green icon, that means everything is good. Yep. And here it shows the addresses as well that I am currently using. Let me open a complete view. Okay. So as you can see, I can modify it from over here as well, and if I turn this on, my output turns on. That's quite good, right? And so as well for my second network as well, it shows P over here, that means peripheral means that are my physical input and outputs addresses, right? And these addresses IW input word addresses that are for my analog input. Now the better way is I will go to sim table, simulation table. I will select these tags over here, push button 1, which I'm going to modify, push button 2. Let me float this window as well. Okay, so let me click over here so that I can continuously modify, and I can just type 0 over here for false, 1 for true, 1 for true, 0 for false, 0 for false, so that you can see over here these are changing states as well. So here, if you have a program, you can look over here. This is quite interesting as well. It works as a push button. So if you have long list of tags addresses, you can call all those addresses tags over here, and you can use them to modify your inputs or outputs. So you can modify it from over here as well. Another thing is you can export, import as well. One more thing I remember, we discussed tags, right? So here are the tags. I can export or import tags from over here in Excel file. If I export, these tags would be converted into Excel file, and since they are machines that we are programming having 1000 or 1500 tags, for example, I can just click make an Excel of that instead of opening my software, and call all those tags using import function as well. And also you can monitor your tags over here as well. As you can see, these are my tags, and where is my PLC SIM? It's down there. Why is it down there? Okay, now it's better. Okay, so this is my PLC SIM, these are my tags, for God's sake. Okay, great. Now if I click over here, true, as you can see my input and output are true, so I can observe this from over here as well, from the monitor window. So we have created a program, we have created tags, we are using sim table as well. One more interesting thing in sim table is, for example, you have this push button. Instead of push button, for example, I'm using a sensor. Let me rename this. I can rewire rename tag as well. For example, instead of push button 2, I call it a sensor. I change. If I do any changes, this would go on warning mode. It says difference in lower level component. My lower level component is over here. It says online and offline different. That means I've made some changes. What I have to do is I have to download these changes to my PLC, load the program, and I'm good to go. So my PLC SIM is compiling as well. Let me readjust this window to over here. So what I'm going to teach you is the sequence. So what sequence does is, for example, you have a sensor and you are estimating that, for example, you are using a conveyor. A product goes to the sensor and the lamp should turn on that my product has arrived. But obviously, how would you do that? Because either you go to sim table and manually force it, but there can be instances, these sequences can help you to actually mimic the process. What you can do is, for example, you know your box is going to region 5 second, so these are hours, minutes, second. I'm going to use tag over here. This is my sensor tag. It automatically detects over here. Action parameter would be, sorry, I click on 1, true, and over here, yep, it seems fine. So I'm going to use play, and right now, as you can see, 1 2 3 4 5. After 5 seconds, it turns my sensor on. So for example, you are using different sensors or different instructions that you can use sequences to actuate it based on time over here. For example, you are filling tank and 10 seconds your tank is going to be filled. You can use a sequence over here. If you're using a garage door, 10 seconds after it is going to reach the limit switch sensor and you are going to need to stop it. So you are going to you can use these sim table and sequences. One more thing that student confuses timers with these sequences. These sequences are just for simulating your program. Timers are actual functions that are used within the program in the logic. So these are two very different things. Remember that. So in devices and networks, if I go over here, there are three different views: topology, network, and device view. In device view, we were already working in it. It shows my PLC. Okay, sorry. I'm going to select over here. If I'm using multiple PLC, I can select each PLC. Since this is device view, and I can zoom it to 200%. Yeah, that's better. You can see my PLC over here. Everything seems fine, everything is okay. It is showing me devices address as well, input and output addresses, analog input addresses. It is not showing an option over here, but we will discuss. And it is showing high speed counter information as well, slot addresses and everything. So if I click over here, it should we will check on if I click on Ethernet port, it comes over here. So yep, in network view what happens is, if I add a device, for example controllers, S7-1200 CPU, 1212C, yep, and I'm dragging over there, I can, yep, and it is connected through my Profinet interface. Connections means the devices that are connected or accessible to be connected are accessible. And one more thing I wanted to show you, okay, these are devices name which I can obviously change. For example, machine 1 PLC, machine 2 PLC. Okay, yeah, show address labels. So now it is showing me IP address of first PLC, IP address of second PLC. So this is my network view that I can use to connect different devices, to connect them together, or connect them on different network. For example, I'm using 7-inch HMI, come on, and I drag over there. For example, I'm using S7-1500 as well. Right, I can change this network as well just by putting 3 over here. Now this is 192.168.3, that suggests the subnet. That means these both are on the same network, and these both are on the separate network. And the last node parameter shouldn't be the same, because it would be a conflict. Then what I can do is further, if it just allow me, I want to show you something. Ethernet switches, come on, just give me one. So now okay, now it's working. By clicking connection, connect to the same subnet, obviously. It is automatically giving me an option, right? So I have connected 2 networks. I have took one scaling switch as well, which I haven't connected yet. So in network view, I've connected those devices, and in topology view, you can just see the devices like that. For example, I'm using PLC, it shows 2 connectors over there. In scaling switch, it shows all the ports over here, because this switch works on one single network that's over here, but it has different ports to be connected. So the topology view actually shows the actual connection between these devices, and network view shows the network based connections. And since we connect these devices to a network, we join over there, and we can make actual connections over here as well. Come on. So only this one is currently online. So because I can only use one PLC SIM over here, so it is showing me the status over here. So you can use a topology view to troubleshoot it, and we will further check it in advanced programming. So now that we have studied most of the important functions, let's see further. So in this lesson we are going to discuss how can we add IO modules in TIA portal. Let me select this from over here. Yep. So here are some signal boards. We already discussed CPUs and when we were discussing network and topology view. Since we are working on device views means this is my rack. Not rack, actually it's our drain rail. As you can see behind, this is drain rail where our PLCs and devices are plugged in. So since my PLC does not have analog output, what I can do is I can put signal board on top of there. So now it says over here out analog output. It's one output, 12-bit output, so there are two registers, QW80, QW81. If I have to add further modules, for example, my application becomes bigger, I don't have more analog IOs or digital IOs, I can, sorry, these are signal boards. Here are digital input, 8 input module with 24 volt DC. And if I click over there, you can see detail information over here as well. It says some IO-Link master. IO-Link is a point-to-point network device. I can add over here. It says for weighing machine. When you click it over here, it becomes blue. That means I can add over here weighing module, load cell, analog output module, right? And for example, this PLC does not have Profibus, it has Profinet, so I can use Profibus module over here. I can communicate it, for example, with S7-1200 or other Profibus devices. We already checked technology module, so yep, this is how we can use our add modules, IO modules. As you can see now, all these local modules are shown over here as well. And if I click a module and press Alt plus enter, it would take me to its properties as well. Right, and these tags are being shown over here. So this is second, third, fourth, fifth slot as shown over here. So if I take this online, Let me remove this. It looks okay. Yep. So I have done hardware changes as well, and now all modules looks okay. I can even use it now in programming as well. So I almost forgot that. I thought we can't use this in PLC SIM, but we obviously can use these external modules and simulate larger programs as well. It still shows some error different in lower level component. I am not sure. um we can check this later on, that what could be the issue. So yeah, that's how you can use IO modules and configure them as well. Like if physically in your PLC these modules are connected, you can uh, configure like that, download the hardware changes, and it should work. Now what I'm going to show you is how you can archive and retrieve a project. Let me take this online. Let me first of all save this project. Okay, by saving this project, it would only save like it would save all these files, right? So I'm saving this project, but if for example you have to send me a project that look aways, please test this, or you are having some issues, or if I have to send you some program, obviously I wouldn't send you all these files. What I would do is I would go to project, archive this project, demo in English, and archive. So I actually didn't see where it's saved. So always it's in my user documents automation. Good. Now what I can do is I can close this, and for example I have sent you that program. Okay. Okay, now I'm going to click on open, retrieve, demo in English. Here's my saved or archive project, right? I'm going to click on open, and I have to make another folder because it is going to extract all these files that we saw in that project, right? Demo, not Tammy. Also, I'm a huge fan of Tamil Water. In anyways, Tamil English retrieved. Okay. So now it will save, extract all those projects files as well. Here's my program fully loaded. So if you are working remotely as well, you can use this archive and retrieve function. You can use TI portal shortcuts as well. Go to settings, options and settings, and here are the shortcuts. So try to go through these of shortcuts. Like I'm using Alt plus enter to open properties most of the time. This is quite common. Open editor, Alt control left and right, create, So these are quite interesting, you know. Try to go through that, use less mouse and more keyboard. So the best thing about TI portal is if you go to the instruction, you can see each instruction details in this help menu. And not only that, if you look closely over here, it has almost everything. It's like a complete book, you can say, a complete manual. I have shared a PLC manual as well, but it has almost everything over here. For example, if I go to TIA portal, um, or yeah, programming the PLC, that would show a good example. Like you can see, creating ladder, FPD, STL, almost every language is covered over here. Working networks, rungs, and there are even some projects or some simple examples as well that you can use over here. So it's quite good. You don't have to jump here and there and Google everything. So most of the things would be available here as well, and you can use further S7 manual. So as you can see, there are basic instructions in all languages, timers, counters. If I go to timers, each instruction is over here, and like that, bingo, and it shows an example as well. Assalamu alaikum, this is Rana Muhammad Awais. This is my S7-1200 trainer board, which I'm going to use in my training. So these are my multiple inputs that have emergency stop that installed on our machine in case of emergency, which we use. These are push buttons of this is green color for start, red color for stop, and these are our selector switches for auto manual mode. This is input plug for power, providing power or to perform sourcing wiring. Here this is my line and neutral options, that means 220 volt and neutral. And here on the right I have 24 volt and 0 volt plugs. This is my breaker, which is used to turn on the power, and below down there is my socket as well. This is my power supply that is accepting to 220 volt, converting into 24 volt and providing this power to the PLC. This is my trainer board's plugs, L plus M ground. So we are going to do this wiring ourselves, and similarly for below outputs as well. This is my main PLC S7-1200. This is the heart of our trainer. This is the Ethernet port connection. Here's how I can plug this. Here on the right I can install external modules as well. So this is how it is cut. So that this is my IO link device that we are going to use in SCADA systems and advanced PLC systems. Below down there, here are some relays of 24 volt or 220 volt. These are switching devices that we are going to use to operate different outputs. These are my outputs, 220 volt AC and 24 volt DC output. These are multi-stated indicators. So this is a quite simple and easy to use trainer boards having multiple inputs and outputs, and we will interface both digital and analog sensors as well, and we are going to have some fun with it and program it. Now we are going to power up this Siemens PLC trainer board and Siemens. Here I have a plug of 220 volt. So this is my power cord is already connected. I will turn off the breaker just in case. This is my PLC works on 24 volt DC. So I have to put over here on L plus M the 24 volt 0 volt. On the right side I have two cables that have 24 volt DC and ground. So I'll simply connect this like that. L plus is my 24 volt positive. On M it is 0 volt DC. So my circuit was completed. From here I'll switch on the main switch and then I'll turn on my breaker. Now I'll turn on the breaker and you can look at the indication that it is being powered up. It will blink for some seconds and then the green light would be stable on my PLC. So like that. Simple, right? In the next lecture, we are going to see how about in detail about these status indicators. Hi, so this is my S7-1200 PLC that have multiple indications over here of inputs, 6 inputs and 4 outputs. So these are indications that are available, and it has 2 analog inputs as well, but those doesn't have indication. So let me zoom this out. You can see over here I can use a signal board over here, for example, of a few analog outputs. Below there they are, you connect output wiring over here of output actuators such as indicators. Here it is my Ethernet plug, Ethernet connector. Over here you can see indications as well, run, stop, error and maintenance LEDs. So let's discuss this in detail, because if you power a PLC and you don't get a stable green LED, that means there's something wrong with the PLC, right? So solid yellow indicates PLC is in stop mode, solid green indicates PLC is in run mode, working perfectly. So when PLC is run, machine is run, PLC should come to run mode. If it is flashing, alternating between green and yellow, that means CPU is in startup mode. So it needs some time. So this is our first indication. Second indication is of error. If it is flashing red, that means there's an internal error in CPU, error with memory card, or a configuration error, mismatch modules. A small simple example is if you have installed an external module and it is not detecting, so that means it will flash. Other than that, there's solid red indicates, that means defective hardware and you have to replace that PLC. Maintenance LED है, sorry, it has maintenance LED. If you insert a memory card, CPU changes to stop mode. After the CPU has changed to stop mode, perform one of the following functions to initiate. So what are these functions? It means CPU change to CPU to run mode, perform a memory reset, power cycle up. So other than that, if you watch force and wash tables, it would come to maintenance mode as well. So other than that, there are status LED table as well. You can check this in the manual so that it would be easier for you to troubleshoot. This is my some detailed specification of S7-1200 PLC that I'm using. So I'm using CPU 1211C. We are going to program it using TIA portal. There are inputs, outputs, Ethernet programming cable going to be used available है, जिसके ऊपर आप कोर्सेज कर सकते हैं PLC, HMI और SCADA पे। और यहाँ पर मेरे YouTube चैनल पे जाके सब्सक्राइब कीजिए और ये फ्री लेसन्स और ट्यूटोरियल्स आगे कीजिए। Now we are going to see how can we connect our programming laptop with our PLC. If I show you over here, this is our PLC. First of all, I'm going to plug my simple Ethernet cable which uses RJ45 connector like that. And second end, I would connect at my PLC programming laptop. So it can be a computer, it can be a simple laptop that have an Ethernet port, right? So you can see Ethernet indications starts coming in. So that means my laptop is communicating with my PLC. So this has receive and transmit LEDs. If I focus a bit more, so by default my CPU has an internal IP of 192.168.0.1. The starting 3 are the subnet that suggests that it is a one network, and one suggests it is a node, a number of devices. So if it's my PLC 1, it can be called here I would type 1. If I have multiple devices, PLC or HMI, it would start counting as 2, 3, 4. And if my laptop, I have put node over here 100, so that it wouldn't conflict with my any PLC devices at its takes starting addresses, right? So I can keep it 200, 201 as well, so that it doesn't go in conflict. But it is on the same network, and subnet mask are the same. That means we are working on the same network. So sometimes you would have a requirement where there are multiple networks running, right? There are two to three PLCs running. So for example, instead of 0, I can here type 10 for a separate network. So let's take it online. Let me first set the IP address in my Ethernet adapter. So I would go over here, I'm using Windows 10, change adapter options, and here I'll click on properties. This is my Ethernet adapter where my PLC is connected. I would go to IPv4, and here you can see that my IP is all fine. So it looks perfect. Instead of 100, I have put 200. And the same process is followed for other PLCs as well, like Allen Bradley, which has Ethernet IP, right? So similar procedure is happening over there as well. So now I'm going to use TIA Portal version 15 as an administrator. So my software started up in online and diagnostic. As we learned earlier, I can check accessible devices from over here. So it would show me if my PLC is connected and communicating or not. So it says Profinet Ethernet interface, Profinet interface. Below there is my Ethernet card. I'll start search. And you can look down there, it says found accessible device. So that means it's mission successful. My PLC is communicating. So you can be directly connecting as well. You can use router as well. You can use scale and switches as well. It would just detect my IP. Right now it's taking time, but yeah, now it is showing complete details that PLC1 is my name. Here's my IP. We can change that later on as well. It shows model as well. For example, if my IP was different than my computer, a network was different, it wouldn't read it. It would show an error. If I flash LED, it would show the LEDs blinking at my PLC as well, like that. So that means it is transmitting information as well by flashing LED. So it is receiving and transmitting as well. In case it doesn't flash, that means my computer is not sending information to PLC. That means something is wrong. Further, I can't do anything from here. It just shows me the accessible devices. I go to create new project. As I told you in TIA portal section, we will name it S7-1200 overview and click create. Let me configure my device. I would go to controllers. It's my S7-1200 CPU, 1211C and 3 times TC. So this is my version and article number that is written on my CPU right side as well. If I show you, it shows on the right side, which is currently not visible because I have connected the PLC. Firmware version is 3 and I'll click add. Here's my CPU. I go to my project tree. Let's check it in online and diagnostic. Let's try to take it online from here without doing any programming right now. I'll just click online. and it's looks perfect. So when I take it online, all comes green over here. Some parameters right now looks orange like that, difference in lower level component. That means my programming that is in PLC and that is in software are different. अभी automationplay.com पे जाइए और ऑनलाइन कोर्सेज कीजिए PLC और IIoT पे, जिसके ऊपर डिफरेंट फ्री और पेड कोर्सेज अवेलेबल हैं, जिसके ऊपर आप कोर्सेज कर सकते हैं PLC, HMI और SCADA पे। और यहाँ पर मेरे YouTube चैनल पे जाके सब्सक्राइब कीजिए और ये फ्री लेसन्स और ट्यूटोरियल्स आगे कीजिए। So in this tutorial we are going to download a program. Let me download write a program. I'll have to take in input contact where I'm naming it as I0.0 and output as Q0.0. So it's written in main. I'll click on download button from over here. So it would compile the program. In case of any error, it would show in below window. There's no error. Let me select this option and stop all. So I have to stop all the modules, click load, so that it would load the program, and now it would continue with download process. Click finish. So it's all green now, so there's no difference in lower level component anymore. I'll click on the classes to test my logic. So this is how a simple program is downloaded. I'll take this offline, and we are going to check the upload side as well in the next video. अभी automationplay.com पे जाइए और ऑनलाइन कोर्सेज कीजिए PLC और IIoT पे, जिसके ऊपर डिफरेंट फ्री और पेड कोर्सेज अवेलेबल हैं, जिसके ऊपर आप कोर्सेज कर सकते हैं PLC, HMI और SCADA पे। और यहाँ पर मेरे YouTube चैनल पे जाके सब्सक्राइब कीजिए और ये फ्री लेसन्स और ट्यूटोरियल्स आगे कीजिए। So how we can upload a program from PLC to PC? Let me go save this first, and let me go to new first, name it upload. So now I'll go to add new device, and since I know it's S7-1200 PLC, we have two options. Either I select the PLC that I know of, obviously, or if I don't know, I can choose unspecified CPU below there if I don't know the article number. So in first step, I'm going to select the PLC that we have, assuming that we know the information. Now I click on online, start search, and click on go online. So now I click on upload from device. So I'll click over there and continue. If I go to program blocks, now my program is successfully uploaded. Simple, right? So now I'll go offline and let's test one more method. Let me delete that device. I'll show you the second method. Add new device and go to unspecified CPU. Now I go to over here, detect, and start search. So it detects my PLC. I select detect, For some reason it did not work. Let me try that again. I'll go to an unspecified CPU, and for firmware version, if I don't know, I'll keep it lower. So when I keep the lower version over here, even if I have higher version, it would detect. Not just detect, I mean it would select the device as well. Earlier it did not. So let me click on detect, and now you would see finally my PLC has shown up. I click on online, start search. Now it's a similar process as earlier, and go online, and now click on upload, continue, and upload from device. So now the main program, it's uploaded. So this was the second method that we have used over here. There's one more method that we can use. Let me show you that. If I go to online, upload device as new station, and click on search. So without adding anything, I'm directly adding the device, but it would show an error. Why? Because it is my old module, old CPU, so it does not support direct uploading. So I have shown you the two options already. You can try that. If you have the CPU that supports that, you can use this method as well. Thank you. अभी automationplay.com पे जाइए और ऑनलाइन कोर्सेज कीजिए PLC और IIoT पे, जिसके ऊपर डिफरेंट फ्री और पेड कोर्सेज अवेलेबल हैं, जिसके ऊपर आप कोर्सेज कर सकते हैं PLC, HMI और SCADA पे। और यहाँ पर मेरे YouTube चैनल पे जाके सब्सक्राइब कीजिए और ये फ्री लेसन्स और ट्यूटोरियल्स अवेल कीजिए। Hi, this is Rana Muhammad Aviz from Automation Play. Today we are going to discuss wiring of S7-1200 PLC. So there are four methods of PLC wiring. First, let me again give you an overview small. There are 6 inputs, 4 outputs. This is my CPU model written over here. These are my status indicators. There are some specs over here, software as well. So 1200 PLC, as we discussed, is for medium, small and medium range applications. This is my 24 volt DC supply. This is inputs. This is 2 analog inputs as well. These are some outputs. There are 4 digital outputs where we have to wire. This is my Ethernet interface, and this is my communication indicators. So this is our CPU. Let me zoom it. So I have already connected my PLC with my computer as my indicator light is blinking. So let's review wiring. This is my 24 volt DC input. I'm using DC, 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 DC power supply, DC input, and DC output. So this can be AC as well, depends on model. So there are different methods to wire a PLC. If I put positive on 1M, so it would be source mode, and negative, it would be sync mode. So this is my PLC inputs buttons. So if I have multiple inputs, I can use separate supply, and for transistor based output, 3L plus 3M, positive negative supply, and outputs there is positive coming out from the PLC. So let's further check it. So first of all, we have sourcing input and PN. That means current flows from PLC to external devices. So if I have L plus and 1M, I have put L plus on 1M. That means all inputs internally have 24 volt. that is being pushed to the input devices, and from the outer end I have 0 volt connected to complete the potential. Input addresses in Siemens are I0.0, I0.1. So for first push button I0.0 and so on. From syncing input PNP, so on 1M it is 0 volt connected to it. So everyone gets 0 volt internally, 24 volt outside. So current flows from external devices to PLC. So wiring depends on the sensors we have connected, and in PLC we are using optocoupler inside internally. So if there's a surge or short circuit, since it's a photo LED, the LED would get damaged, but phototransistor would stay safe, and our processor circuit would stay safe as well. So it's output wiring 3L plus 3M, 24 volt 0 volt directly connected. From internally 24 volt supply is being provided because it is sourcing output circuit. Outputs uses a optocoupler as well, so it provides optical isolation over here as well, so that my internal circuitry stays safe in case of short circuit. So addresses are Q0.0, Q0.1. So this is my module, and these are my bits, byte and bit. So transistor output can provide up to 2 amps, used for servo motor, stepper motor applications to generate PWM signal. And if relay output, it can provide up to 10 amps for external relays and contactors that operates motor, right? So relay can provide 220 volt, 110 volt as well, or 24 volt. If I have a different CPU version, so normally it is written 1N over here, that means it can be sourcing output or syncing output as well. So for sourcing output, in previous we had 3L plus M, 3M. So for 1L I will connect 24 volt, and that would provide all that internally to output, and at the outer end I would connect 0 volt. 0 volt at 1L and syncing output, and from the outer end I'll connect 24 volt. So, okay. So let's check on our trainer board. So how my wiring is connected to one. On 1M I have connected 24 volt positive, that means it's sourcing input, and to 0 volt I have connected to all my input devices. So my red is 24 volt positive, black is 0 volt, and my power supply is connected from previous end to all these plugs at the outer end. So input has 0 volt, 24 volt as 1M, as you can see over here. And on buttons I have connected it to my inputs I0.0 and I0.1. So let me show you on the zoom by doing zoom. So buttons are connected in this way so that my circuit gets completed. These L plus M are empty. This is a supply that PLC generate, but we don't use it because number of access inputs can reduce internal PLC supply. So I'm using external PLC supply to provide on my inputs. So let's check the output wiring as well. Let me zoom out. I have sourcing output 3L plus is 24 volt connected, and 3M is 0 volt connected directly. And at lamps, as you can see, Q0.0 is going to my most right lamp, as you can see over here, and at the outer end my black 0 volt is connected to complete the circuit, because internally the 24 volt is being provided to outputs to my PLC. So we will further operate it. Let's test just one more time. Let me zoom that a bit as well. So everything looks good over here. Let me zoom out, and if I turn on the CPU, my lab get turns on, and by pressing the off button it would get turned off. I have done latching in my circuit, as you can see, so everything works perfectly. So I'll explain further the latching process and other bit logic instructions and programming as well. So stay tuned and thank you. अभी automationplay.com पे जाइए और ऑनलाइन कोर्सेज कीजिए PLC और IIoT पे, जिसके ऊपर डिफरेंट फ्री और पेड कोर्सेज अवेलेबल हैं, जिसके ऊपर आप कोर्सेज कर सकते हैं PLC, HMI और SCADA पे। और यहाँ पर मेरे YouTube चैनल पे जाके सब्सक्राइब कीजिए और ये फ्री लेसन्स और ट्यूटोरियल्स अवेल कीजिए। So let's see diagnostic buffer, which comes from device and configuration settings. Here you can see they are different errors or events are showing. Further, in set time option, I can set time as well. I have updated that. And so what diagnostic buffer does, whichever errors, alarms or diagnostic events, startup events, so it would display all these information over here, all the internal errors over here, so it would be so easier to troubleshoot. Other than that, this is memory, this is my IP, this is my ports that is being connected, my computer is connected to. I can assign my IP address, change my IP address. We have already discussed the time as well. We can reset the PLC over there, and from here we can configure or assign a profit device in, because if we have multiple PLCs, we can check the name. So here, if I press Alt plus Enter, let me drag this over here. So if I press Alt plus Enter, it would show me the properties. Here it shows green. That means my PLC is obviously online. Let me go to properties now. Oops, why I keep doing that? Okay. So here, project information, Ethernet options as well. Here IO tags that we discuss in TI portal section as well. For my S7-1200, it has limited options, so we can't connect output modules to the right side, but there are 3 modules option or at the left side. So other than that, on left side, as I said, I can connect communication modules. So communication modules are connected on left side and IO modules on right side. और SCADA पे, और यहाँ पर मेरे YouTube चैनल पे जाके सब्सक्राइब कीजिए और ये फ्री लेसन्स और ट्यूटोरियल्स अवेल कीजिए। Assalamu alaikum and hello everyone, this is Rana Muhammad Awais from Automation Play. In today's tutorial, I am going to perform latching in S7-1200 PLC, basically using bit logic instructions. So this is my PLC input circuit and output circuit. I have connected this on sourcing mode, as you can see over here. On output, it is 0 volt internally, it is providing 24 volt. So I have connected 2 push buttons, I0.0, I0.1. On output, I have connected 1 lamp on Q0.0, as you can see, and it is sourcing circuit as we discussed earlier. So we have already explained the wiring. Now schematic diagram is, I have 24 volt to my 2 push buttons ongoing. Start stop push button, there's a coil output lamp, and this is coil in series, in parallel as well, to latch the circuit. So you can see the ladder diagram over here as well. So I'm using 2 contacts, normally open, normally close, 1 coil, and the contact of that coil in parallel. So I have done this diagram on Automation Studio as well. Let me simulate that. So when I press the push button, 8 volt, it latched my circuit. It is a momentary push button, right? So when I press the stop push button, it would delatch my circuit. So this is how it works. So let's perform this on TIA portal. Let's create new project. Let's name it Latching. Let's add new device. Let me add my CPU. So let me go to main OP where we can program our PLC. First, let me put up the tags as well. So let me name start, stop, and 1 for output. Output, let me change it to Q0.0. 0. So that looks good. So now let me go to main OP. It would take some time. Okay. So now let me take contacts input and normally close output as well. Let me use the tag start. Here I am going to use stop, and output, for some reason my cursor is not showing right now. Sorry for that. My cursor is actually stuck. I'm not sure why. Okay. So I take the branch over here and name it Q output address Q0.0. So now my PLC is already wired. Like we discussed earlier, it's in sourcing input mode and sourcing output mode. So everything seems good. My PLC is connected to PC as well. So let's download this program. Let me put my adapter over here. So I'm using my laptop as well, and sometimes my computer as well. My computer has TIA Portal version 14, laptop has TIA Portal version 15. So there's some small similarities, but don't be confused. So let's compile that and go to no action, stop all, similar practice, and finish. So let me take it online. So everything looks green over here. That means everything's okay. So let me show my webcam first. Turn on the monitoring and let me bring it up my webcam and take the windows side by side. So if I press my green push button, you can see the output indication turned on the CPU. And on my programming laptop as well, in my software as well. So let me stop that, and as I stop, my output coil turns off. So this is how latching is being done. Now my output state is being maintained by using contacts input and contact latching. If I remove that, for example, and then download it, so if I press my green push button, so my light is on. As soon as I release it, now it's maintaining state. As soon as I release it, the output would get off, right? So because these are momentary push buttons. So it's important for latching to maintain our output state. Let me put that contact again, download the program, and let's test it one more time. I'll turn my push button on and turn off, but it would state the maintain. You can see below my beautiful lamp as well. Thank you. अभी automationplay.com पे जाइए और ऑनलाइन कोर्सेज कीजिए PLC और IIoT पे, जिसके ऊपर डिफरेंट फ्री और पेड कोर्सेज अवेलेबल हैं, जिसके ऊपर आप कोर्सेज कर सकते हैं PLC, HMI और SCADA पे। और यहाँ पर मेरे YouTube चैनल पे जाके सब्सक्राइब कीजिए और ये फ्री लेसन्स और ट्यूटोरियल्स अवेल कीजिए। Assalamualaikum and hello, this is Rana Muhammad Awais from automationplay.com. In today's tutorial, we are going to do our first exercise of box transfer using obviously Factory IO and TIA portal. Let me open Factory IO software, and this is my exercise 1. This is box transfer exercise. Let me use Coil tags. You can see photoreflector sensor retroreflective, which is using reflector, and IR light is being reflected from that. If any object passes through it, it would send a signal to me. It would disconnect that signal, so obviously I get a signal. So it uses sensor and a motor. It transfer a box till it reaches a sensor. So we have one input, one output. Retroreflective center address is I0.0 and motor that runs the conveyor is Q0.0. So this is bit lodging instruction. We are going to use contacts and coils. So let me delete that program. Software and template is already open. So if I'm using version 14 in this exercise, you can use version 15. If you are using, you have to use version 15 template. So I'm using, let me add tags. Let me name it as sensor and output as motor, and delete that tag. Let me go to main. Let me give my input as sensor and output as motor. So I'm using normally open contact because sensor is already sending me a signal. So as the signal arrives, my conveyor would start running. Let me download the program. So if Factory IO is a great software, I mean you would be programming as we program in the industry, right? So those professionals who are attending this course would know that. Let me take this online. Status is all green. There's no error, which is a really good sign. Let me turn on the monitoring, and let's take the screen side by side like that. So I would play now. Let me reconnect it. Sometimes gets disconnected. So let me separate that and click on connect. So I'm using PLC SIM, and I would click on the start button. So as I play it, you can see sensor is providing signal to motor. As soon as it reaches, it cuts off the motor. Let's operate it again. So I'm using normally open contact for sensor. Do understand that. So as soon as it reaches, it disconnects the motor. So logical continuity has taken over here. So we would further perform different exercises. You can use different functions as well in this exercise as well. अभी automationplay.com पे जाइए और ऑनलाइन कोर्सेज कीजिए PLC और IIoT पे, जिसके ऊपर डिफरेंट फ्री और पेड कोर्सेज अवेलेबल हैं, जिसके ऊपर आप कोर्सेज कर सकते हैं PLC, HMI और SCADA पे। और यहाँ पर मेरे YouTube चैनल पे जाके सब्सक्राइब कीजिए और ये फ्री लेसन्स और ट्यूटोरियल्स अवेल कीजिए। Hello everyone, this is Rana Muhammad Awais from automationplay.com. In today's lesson, we are going to learn about set and reset bit logic instructions. I'm going to use S7-1200 PLC on TIA portal. So from here, we can select our bit logic instructions. Here I will drag set instruction, or first I'm going to use some normally open contact, and then from here this window I'm going to select set instruction. Let me put the address over here of I0.0 as input, and from here let me put Q0.0. So I have taken one normally open contact that upon pressing the push button it would set my Q0.0 bit. So it's a retentive function, and now I have to use reset as well. So first I'm going to use normally open contact once more, that I'll put address as I0.1. So this is my trainer board. As you can see, I have two push buttons on top. Green is my I0.0 and red is my I0.1, and then I have a lamp as well that is connected to my Q0.0. This is my power going on from over here, and this one is on 24 volt. So above is 0 and below there it's 24 volts, so it's connected on source mode. So over here I'll take one reset reset coil, sorry, and name it Q0.0. So I'm going to use the same tag as I've used for set, because it's the same bit that is being set and reset. Let me put tag names over here as well. It's always good to use tag names so that you may remember what uh, addresses you have used, right? So all tags are done. Let me download the program in my physical PLC. Let me turn on the monitoring, and from the trainer board now, if I press the green push button, upon pressing and releasing it, my output bit is output lamp is kept on because it's retentive. Upon pressing red push button, the light has turned off. So this is how we can use set reset instructions in TIA portal. Hello everyone, this is Muhammad Awais from automationplay.com. In today's lesson, we are going to learn about set reset instructions by implementing it on factory I/O. So this is the exercise that we are going to perform. This is my factory I/O software that I had explained in the software setup section. I'll select the exercise from over here, A to B exercise. I'll go to driver, S7-1200. Since my physical PLC is connected, if I'm using PLC SIM, I'll select PLC SIM from over here. Otherwise, I use S7-1200 PLC. Right now, my physical PLC is connected. I'll take bool inputs and outputs as 10 so that it doesn't conflict with my initial addresses, because physically my buttons or lamps are connected and it would conflict with that. So I'm using 10 addresses, so it would start from I10.0, Q10.0, right? I'll click on connect. It would show the good green symbol. So this is my green exercise. There's first conveyor, which is my entry conveyor. it is force conveyor, it would automatically start, and as it touches the sensor, the next conveyor, the main conveyor, would start or set. And there's a sensor at the end as well. It would keep running until it reaches the second sensor over here. So we are going to use set and reset instructions. So one more thing, it is set to reflective sensor. So in idle state, it's already giving the signal, high signal. That means on touching the box, it would send me the low signal, sorry. So let's check into that. For that purpose, I'm going to use normally close contact, the opposite one. It's I 10.0, it should be I 10.0. From over here, I'm going to use Q 10.0. I'll assign tag names as well. Let me correct that first. I 10.0. So I've taken I normal close because it's sending the signal in idle state. So if I take open contact without box without reaching a sensor, would already set the conveyor, right? So as soon as box reaches the sensor, it would turn off the sensor and my normally close contact would be on. So it would set the conveyor. Now I'm going to use normally close contact for the other sensor as well. It's sending a signal in idle condition, and so upon touching the sensor, my normal close contact would be active and it would reset this conveyor. So the main conveyor should start upon I 10.0 and reset upon I 10.1, right? Let me download the program. So mostly we use rising and falling edge instructions, which we are going to use ahead. But right now, to explain the contact base, I'm using that. So now it's not sending signal, but as it touches the sensor, it sets this conveyor. It goes till it touches the end sensor, second sensor. As it touches the sensor, my conveyor has been reset. Let me play it again. It's not setting the conveyor right now. As it touches the sensor, it sets my conveyor, and as it reaches the second sensor and touches it, it resets this conveyor. So it's working like that. We can use set reset instructions, and we are going to use same exercise with bit rising and falling edge instructions as well. Thank you. Hello everyone, this is Muhammad Awais from automationplay.com. In today's lesson, we are going to learn about rising and falling edge instructions. So as we had used contacts earlier, we are going to use rising and falling edge in our TIA portal and S7-1200 PLC. So here I have already selected my PLC, and from the right side where I have basic instructions, this is my trainer board where I'm going to use green push button and red push button for this purpose. So here are my rising and falling edge instructions which I'm going to use. Let me drag this over there. Before that, you can see the description of each instruction over here as well. So here it explains in details about the positive edge and negative input signal edge, as you can see in the picture. So how positive negative edge works is when you press a push button, it gives a positive edge signal, and when you release it, it gives a negative edge signal, right? So this is how it works. So as we saw earlier in the exercise of factory IO as well, We can use those signals over there. First, I can select open contact and make it positive edge. So when I press my push button, my output should turn on or should be set. And when I release it, it should my lamp should turn off. So let me use a coil first. Let me use set instruction over here. Let me put I0.0. Let me put over here Q0.0. Take me one more contact for stop push button I0.1. Over here I will use contact, I'll let you know. So I will use a memory bit over here which stores the last RLO state, last state of my input. If I show you over here, here is the contact tag in that is being displayed over here as well. So it stores the previous scan in the H memory bit. I'll use a contact over here as well. I'll name it reset and use the same address as Q0.0. I'll download this to my PLC and turn on the monitoring. Now if I show you my trainer board over here, when I press the green push button, my bit is set, and if I press this red push button, my bit is not getting reset because I have put negative edge. As I release it, it resets. So set, and upon releasing the red push button, it gets off. So this is how positive and negative edge works. And we normally use this for sensors, like start of the conveyor we can use positive edge, end of the conveyor we can use negative edge, like that. Now let's further use trigger bits, positive and negative edge trigger bits, right? Let me take two inputs, I0.0 and I0.1. Let me connect this branch. So I have this positive trigger. Let me show you its detail as well. Positive trigger, scan RLO for positive signal edges. So it would scan all the input signals, and as it gets positive signal, it would enable the output. So that's how it works. Let's perform it. Let me give auxiliary bit that would store the previous edge memory, previous signal, sorry, and let me give one output over here, Q0.0. Let me delete earlier program and download this to my PLC. So earlier we had used positive and negative edge, that is used at the extreme left, right? And this is used in the middle. If I press the push button, it gets a positive signal and it turns, as you can see, the result M0.0 as true. Let me use this as set because it's just sending a pulse signal. Let me turn on the monitoring and if I press my green push button, my output is set now, as you can see in the trainer board as well. If I use over here negative trigger, let's see how that works. So if I press, let me just edit that. Okay, because that bit is set, let me take one more block, name it I0.0, I0.1 for the stop push button. Let me delete that from over here. Let me take positive trigger over here. Above there I have taken negative trigger. Let me put this to reset, because as you can see in my trainer board, my lamp is currently on. So these trigger commands are used in the middle, can't be used on the left or the right. So let me download this to my PLC. It's already set, so let me reset it by I0.1. As I click it, it's positive and it turns on, off, sorry. So it's programmed on negative edge, so it should work on release. If I release this, my output turns on. So because it's a negative edge signal. Other than that, there are different other functions as well. We can use that as well, which have separate inputs, separate clock signal. And the signal that has to be sensed can be put over here in the clock. And for these functions, I'll perform on factory. Hello everyone, this is Muhammad Awais from automationplay.com. In today's lesson, we are going to perform rising and falling edge instructions in factory IO. So let's check factory IO. Let me select the exercise. We are going to perform scene 2 that we earlier performed. We had already used set reset instructions. Let me dock all tags. So what's important is to note that since we use rising and falling edge instructions, this sensor is already in idle condition giving a signal. So that means it is already giving a positive signal, and so as the other sensor. Since it's already sending this signal in TIA portal, I am going to use a negative edge. Let me show you in this diagram as well. Here. So this positive signal the sensor is already sending us. So upon when the box touches the sensor, that means it gives the negative signal, negative edge signal. So if I have to set the conveyor, I have to use negative edge in TIA portal to set my conveyor. So it's important that you understand this concept. So at the end, sensor is giving me the positive signal as well. But at the end, its positive signal is already giving. So if I if my box touched that, it gives the negative signal. So let me show you over here. Let me take a normally open contact and let me take negative edge over here, or I can select it from the right as well. Let me give the addresses 10.0 since I'm using physical PLC with factory IO. You can use I0.0 on simulation. Let me give this bit and let me give the address for output as well. Let me make it to set, and output as Q10.0. Similarly, I10.1 for my second sensor. Let me define the tag as well. So the same conveyor would set reset. Let me for now give its negative signal as well. Let me download this program. It shows some error. Oh, I missed that bit. Let me take M0.1 over here and download the program again. Also, I should take a reset bit over here and download it. So I'm making silly mistakes. Okay, let me connect my PLC over here S7-1200. Let me give over here 10 and 10. Let me connect that. So let's try it. It would give me this signal. Let me drag this a bit and turn this on. So on negative pulse my conveyor is set, and if it touches it is reset. So as the box touches it gives negative edge signal, and we are using negative signal in TIA portal, so it works. Let me try giving it a positive pulse on the second sensor, because if I keep positive pulse on the first sensor my conveyor wouldn't just be set, because it should leave the sensor. Let me show you how. On the start it gives negative edge, and so it is giving positive now. It would on touch it would give negative, and then it passes and gives the positive edge. So my box, instead of stopping on the conveyor, it passed through. So if I'm using other conveyor, I would need positive edge. I have changed that to positive as well. Now let me show you. Now it would only give positive edge signal when box completely passes the sensor, but it's not being passed, so my conveyor is not being set. So if I force it, it would run this conveyor. So if instead of this signal, let me just take a normally open contact and let me take a negative trigger signal. Let me try that, and let me give this as negative edge as well, so that my box stops on the conveyor, and let me download this. Now let's sorry, let's restart this. Sensor is giving a signal, it provides negative edge and conveyor set. And now on the other end it would give negative edge and my conveyor gets reset. Let me dash Test it again. It's true. It shows false. False means it shows negative edge. And now conveys reset. So this is how trigger functions works. In other exercises, we are going to work on timers and counters. Thank you. Hello, this is Mohammad Awais from automationplay.com. In today's lesson, we are going to work on timers in S7-1200, including pulse timer, timer on, timer off, and timer on retentive. So these four timers are available. We are going to check its differences as well, how each timer works or operate and used in different applications. So let's open TIO, sorry, TIA portal. I already have my physical PLC as you can see on the screen. I'll open the main block and on the right side in timer operations, I have all the timers over here, right? So its description is mentioned as well. I will select pulse timer initially. Let me drag it. It will create its own data block that will store its values. So whether you are using timers or counters, it will create a data block. Let me further show you the timing diagram as well of pulse timer and further details by going into the description, right? So here's the pulse timing diagram. As my input operates, my output turns on as well, but my output is on till my preset time value is reached. So this is how timing diagram works. I'll further explain later on as well. Here's the symbol of our all the symbols and details of input and output parameters. So I have to put timer as t hash 5 second or t hash 10 second. At elapsed time, I have to give an output address like MD1, MD2, MD3, like that, because the data type of time is a double, right? So I'll use a code T hash. I can use 10 second or I can use over here 1 hour or 1 day underscore 1 hour, 10 seconds or 10 minutes like that, and 20 milliseconds. So I can use up to 2 days, I believe, in single timer. Otherwise, I will use timer in series to exceed it to 10 days, 20 days, whatever it is. So I've used t hash 10 second and address is MD10. I won't use MW because it is double data, double word data, which is 4 bytes. I'll use input condition as I0.0. I'll rename the tag as start and further I'll rename it as output underscore one. So let me choose my physical PLC. Let me click load. It has asked for assign IP address. If I restarted my PLC or my network address is not fixed, so it sometimes automatically assign as well. So now I have loaded the program. Let me click my push button. As I click my push button, my output is on and my timer has started. I have released the push button, but timer is still going on, and as the value reaches, my output goes off. Let me give a pulse. So it operates on a pulse signal, and my timer has started. It would reach till 10 seconds, and my output goes off. So it operates on pulse, but function is of off delay, meaning output is on till the preset value is reached. Now I will use timer on delay, and further timer off delay, click OK, and timer on retentive. I will put input conditions and output coils with each timer. Let me keep the same input condition. So on the same condition, input condition, my timers would operate. Let me copy and paste that of 10 seconds. Now output should be different. So let me put different output address Q 0.4, sorry, 3. Let me put different memory addresses over here like that. Try to use a space of 2 to 3 addresses. For example, I use double word data, so there should be a difference. Okay, in earlier timers, there was not a reset option because these were not retentive. But in this, I have a reset option as well for retentive timers. So let me download and we will operate these timers one by one. So we already had checked the pulse timer. Let's check timer on delay. On delay means there will be a delay, then my output would turn on. And off delay means output would be on, but after a delay, output turn off. So right now my timer off delay is working, but timer on delay is not working because I have to keep pressing the input condition on timer on delay T on. If I keep pressing button, my timer reaches the value as you can see, and my my output turns on like that. So this was a function of timer on delay. It's not retentive, so it is not storing the value. As I release a push button, it resets automatically. So it is used in application where you have to convert data motor to star to delta. You have to put a delay that after 10 seconds star contactor turns off and delta contactor turns on. Now for off delay, if I press a push button and release it, my timer is operating and my output is on as well. As it reaches, the output turns off. So it is used in filling application. For example, you are filling a tank and you have to you do a timer based filling for 10 seconds. You can use timer off delay, in which output would be kept on and turns off after a preset time you have set. So this output can be given to any valve like that. Timer on retentive. So difference between timer on and timer on retentive is this will store the elapsed time value. This will store the value so that if your PLC is restarted, it would start on the value that it had stopped. So it has a reset button as well to remove the retained value. So as you can see, it is storing the timer value. I have pressed the push button. I and now my output turns on since it has reached the preset value. So this is the exercise we are further going to work on. and we will use the desired timer. Further, you can use multiple timers to practice on different exercises. Thank you. Hello everyone, this is Mohammad Awais from automationplay.com. In today's tutorial, we are going to perform timers on factory IO exercise. So let's open this exercise. Opening filling tank exercise on factory IO. So this is my tank. As we performed timers in earlier exercise, we covered multiple timers. We are going to use the desired timer over here and we will check which is the best timer that can be used in this application. I'll go to options, drivers and select my physical PLC. There are multiple input outputs that are available. I have to display the timer value as well. So I'll don't use it. I don't need it. So we have two push buttons over here, fill and discharge, and outputs on the right side of filling valve and filling indication, and discharge valve on the bottom and discharge light on the panel. So I don't have timer, we will configure that as well. Timer is our T-word double word output. I've given one. I'll use 10 since I'm using physical PLC, otherwise you will use 00 over here for simulating it. I have QD 100, I'll put timer block over here. Great. This is double integer address now. I'll connect it, it's all green. Let's make a program now in TIA portal. I have opened it already. PLC S7-1200 is already selected. I'll use input contact. Let me show you the addresses as well, the input outputs. So this filling button is over here. I'm going to operate fill valve using this push button and its indication as well. Let me give this I10.0 the starting address. So this was my fill address. Q10.0 is for fill valve. Q10.0 is fill valve and Q10.1 is for filling indication. That's an output as well. Oops. Now we have taken normal input and outputs. So I have to use timer based filling. We are going to use timer that turns the output on. So it's a T off timer. Let me click OK to create a data block. It's a system data block. We don't need to do anything else. I am giving T hash 10s. Let me use MD1 over here. Let me name the tags as well. So now uh, I have used timers and use timer. I have a discharge process as well. For discharge, I'll use the discharge push button. That was I10.1. Let me use timer as well. That would be the same timer as the off. Since I am filling for 10 seconds, I have to discharge it for 10 seconds as well to completely empty it. Let me use MD10. I could have used MD4 here as well, but I like to keep the distance. Let me use discharge valve output, which is Q10.2, and for discharging lamp, it is Q10.3. Since my timer output address is QD100, let me put this over here. M was an internal address, QD is a physical address since factory IO is sort of a physical environment for us, physically simulated environment. So let me put QD100 over here. Let me rename it as well. Let me name it as timer value. As you can see, discharge push button is normally closed. It's physically connected as normally close contact, and that one was normally open. So it's giving a signal upon pressed. However, stop button is already providing a signal, and upon pressing it is disconnects it. So I'm going to use normally close over here because if I use normally open, timer would automatically operate. So make sure you understand this. Physically, it's normally close. I want to start it upon pressing, so I have to use normally close over here as well. So let me name it as I10.1. Let me name it as discharge push button. Let me name it as fill push button. I like to create tags by their actual names, so I believe the basic program has been created. Let's download this first and operate how it works. Let me download it to my physical PLC. Let me keep both side by side. So if I press a push button, my timer is operating. It will go on till 10 seconds and then it would stop. There's an issue in this timer value. We will check it. So now if I press a discharge button, it would discharge all the water on 10 seconds. So the timer is showing milliseconds. Fill and discharge is working well. And let me work on further timer value as well. So make it in the range of 0 to 10. For that, if I divide this by 1000, I can convert it to 0 to 10. Other thing also is the value. I have to reverse this value as well so that it shows as 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So let me create a new network. Let me use divide first. My IN1, sorry, my IN1 or input 1 is, let me use MD1 again. Let me put over here MD1 as well. And in the other one, I have to use 1000. Output would go on in M. Let me use MD5 and then I have to reverse the value as well. Let me use subtract simply. So if I subtract 10 from MD5, so the value that is coming into MD5 is being subtracted from 10, so it would automatically from would be in reverse from. So 10 minus 1, for example, would be 9, right? So let me use QD 100. Let me use the filling tag so that it would only show the value when my filling valve is on. Here it is. So when valve turns on, these calculations would be started. Similarly, I am going to create this for my discharge as well. Let me copy this network. Let me paste this here, delete the upper network. Let me use MD20 over here and let me put the addresses accordingly. Let me use a discharge valve signal over here. That was my Q10.2. Let me create a tag name for this. So let me download this and operate on factory IO. Let me take this side by side. So I have done the correction. I have put 1000 over here. Let me operate. So as you can see, It's working as we program for work for 10 seconds and display accordingly. And let's check the discharge as well. It would start from 10, 9, 8, and it's working well. So in this example, we have performed these timers. In further examples, we will further work on different functions and on different exercises. Thank you. Hello everyone, this is Mohammad Aviz from automationplay.com. In today's exercise, we are going to work on counters with S7-1200 PLCs, including counter up, counter down, and counter up down. So I'm using this S7-1200 PLCs similar as before exercises. Let me open TIA portal and PLC is already selected. So let's go to instructions on the right. We have all three counters over here. Let me use counter up. It will create a data block for storing its values. In counter up, we have three inputs and two outputs, right? So let's put a condition over here, which can be our sensor, which can be our push button. So normally we are using sensors to count the values in production, but I will be using push button just to operate this counter. Since counter will store its values, it's a sort of a latched counter, so we have to put a reset condition as well. And then preset value. So I can use a constant value or I can use some memory address as well, or I can put from HML. So as 3 times the button is operated, then my output will be acknowledged. So my output would be displayed in this value, memory address, in which then I can use comparators. And let me use a output as well. So we use counters in counting application, and sometimes we use in troubleshooting purposes as well. Some signals that are not sense, we use count as well. So let me use addresses over here. Now let me assign reset tag as well. So I have used all input conditions. Let me name it as lamp. Let me use global output. We can select different data types. I'm using integer right now. Let me download it and then we will operate it. Let's check its monitoring. If I count up, top of the counter you can see value moving, and as it reaches 3 my output turns on. So you can see 3 as its current value as well. We can further use comparators as well. So this is counter up. I can use reset to reset the value back to 0. This was counter up. Let me take this offline and use counter down as well by removing this output, since I will use same output with counter down. Let me name it as counter up. Let me hide this network and bring in counter down. So this is now counting down. Mostly we are using counter up and counter down together. I mean, we hardly use counter down separately. So, for example, we have a sensor at a conveyor, sensor at the beginning, sensor at the end. So, counter up will be doing the first sensor. First, let's discuss this. So, the LD button, what it does is it loads the preset value into CV. So, it directly loads the three value into CV. We will operate it as well. Let me assign these addresses. So I was telling you that counter up, counter down used are together. If there's a sensor at the start of the conveyor and end of the conveyor, so I will use counter up for the starting sensor and counter down for the exit sensor, like that. So let me use the physical addresses that my push button are connected to. Let me use a selector switch for load. So my circuit is completed. Let me load this. So now let's operate it. As soon as I increase the value, so as I operated selector switch, the counter is loaded with 3. So now I will reduce the value, counter 3, 2, 1. Since load it fills the max value and by using the push button, we reduce the value. Let me use it again. It is filled with 3 value. Now countdown won't work if I keep the load button on. So let me turn this back to off. Now I will use countdown and it goes from 3 to 1 to 0. So this is how your countdown is operating. Let me move the output and now count up down. So as I told you, countdown normally does not use separately. So it is a mixture of count up and down. You can use it in warehouse applications when product is coming in or down, or you can use, as I told you, there is entry and exit sensors in the conveyor. You can use with that as well. So it has both inputs of counter up, counter down, and it has output as well. QD is for Boolean output, CV that stores our actual counter value, and then there is output. So let me assign CE push button, CT push button. There's this reset, and there's this LT. So we have counter up, counter down, reset, and load. So when my product is entering the conveyor, it would be sensed by counter up and has preset values reached. So my output would show some result as well. So as the value reaches to 0, my Q 0.1 output would be on as it reaches 0. So Q is output for basically countdown, you can say. So you can go to help manual to further uh, get the details of this. So one thing that is it's showing that it's high limit and low limit. So minus 32767 6823267. That is the maximum value that can be achieved. So you can increase two counters in series to increase its value, double the value. So now we will operate it. It's showing 0 right now. Q 0.1 is true. Let me count up. Q 0.1 is false. Let me count up once more. And count 3, my output is on. Q 0.0 for count up as maximum value is reached, but it is 0 since it's not 0. Let me count it down. 2, 1, and 0. So Q 0.1 is on and Q 0.0 is off, like that. So you can use counter up and down like that. So in exercise of factory IO, we will perform these counters as well and see in detail how it really works. So you can load and unload different boxes over here. There are two sensors. One will be counting up, will be counting down, like that. Thank you. Hi, this is Mohammed Awais from automationplay.com. In this exercise, we are going to learn about comparators with different examples. We use comparators when we are comparing two values, two addresses, two different variables, right? So if it's equal, not equal, greater than, less than, so we can use comparators. So I already have TIA portal opened over here. Let me create a new project. So I already have a PLC selected. Let's create a main OB. And on the right side, you would see comparator operations right below timers and counters. So in comparators, you would see different options like equal to, not equal to, greater or equal, less, in range, out range, right? So compare is represented by two equal signs, and down below they are angular operators, which is representing not equal with one greater than, less than, one greater than sign, then greater than equal to sign as well, and then less or equal to. So you can use these as per your applications, like that. We have greater than as well, while greater than equal to would be, it would detect the same value as well. Then there's less than, and then there's values within range. If there's values within range, my output would be on. And then there's values out of range as well, which we will use when we do analog programming, right? There are some other functions as well, which we hardly use. This is used if value of a tag is a valid floating point number or not. And then there's QD if the value of tag is invalid floating point number. So let me use this one. I can use POC, and we are going to use counters first so that we can compare different values, right? So let me use set, reset, counter up, reset, and PV values. Let me name it as N0.0. I'm taking memory bits. I'm no longer using my physical PLC right now. So we are just going to work within TIA portal to further perform these instructions. Let me use now equals to sign. Above there, I'll use the output value, the timer, a counter value that is coming in, and I'm comparing it with 1. So if it is 1, my output would be on. Then I will use not equal to. For not equal to, I'm comparing it with 0. So if the value of counter is greater than 1, my output would be on, and that output would be M10.1. So let me hide this network. Let me rename it as equal. And let me rename this as not equal. Now let me use greater than equal to. So now let me use greater than equal to. I will use over here IEC counter db dot cv. So I can use counter values like that. I can either use pv or cv and recall that value from the data block where it is being saved. I was using greater than equal to, and let me compare it with a constant value of um, 3. Let's take it 3. Now let me take less than equal to. I have copied and pasted this, and let me compare it with 2. Let me take an output over here, M10.3, and below there, let me change it to M10.4. That's perfect. This would be less than or equal to. Now I will use simply greater than. Let me create a branch and use less than as well, and let me put the values accordingly. So let me put all the tags over here. Now let me use in range instruction as well and out range as well. And let me use output traces over here. I already had used 10.4, I believe. So let me use M10.7 over here. Or let me use some other address M20.0 so that I don't get a conflict. So I have put over here range 0 to 5, same as above right now, but there will be different behavior of outputs, right? So we will check and operate it. So now my counter is working. Let me operate this one by one. Right now my value is 0. So this one is not operating. Let me put the value representation as decimal. You can change that as well so that it doesn't show in hexadecimal. So right now 0 into 1. Let me modify this. So now since counter value is 1, my output from comparison instruction is operating. And since it's not equal to 0, this not equal to instruction is working as well. As you can see over here, let me hide both networks. And now for greater than equal to, that is the value of 2. So I should modify my counter. Okay, so this one is working because it's less than equal to 2. It's less than 2, so it's working. As you can see, counter value is 1 right now. So let me change it to counter value to true. It would increment by 1. It's 2 now, and it's equal to 2, less than or equal to. So it's working. And now my this function is working as well. It's greater than or equal to 3. So it's equal to 3, that is working. It's not equal to or less than 2. So that's not working. I just dropped my phone. Sorry for that. Okay, now we come back over here to greater than or less than command. So it's absolute, right? So it should either be greater than or less than. So the value, I believe it's 3 right now. Let me modify it. So it's greater than 3. My output is working. This one is not working because it's not less than 2. Now for in range, because the value is in between 0 to 5, my in range output is working right now. For out range, the value should not be between 0 and 5. So let me exceed that. So now my value is out of range. It should be out of range. Yep, now. So it is 6 now, and now out range instruction is working. So in range is not working, out range is giving us the output because it's out of range right now. So this is how we can use in range, out range, and different comparison instructions. We can further create range as well, for example, using two greater than or less than instruction series. Thank you. In this lesson, we are going to work on move instructions. So from the right side, I'm going to use and select move instruction. I've already selected the PLC. So after mass, we are going to use move instructions. Different move blocks over here. The most common is that it copies the contents of the operand at the input to the operand at the output, right? So if I am going to move at values from some address to another address, I can use move value, but make sure it doesn't move the value, just copies the content of that address to another address. So the values in the first address remains the same. So there are different move block, fill block, scatter. We can move, sorry, we can move arrows of data. We can swap the data within the address. So let's use this move address, move instruction. We have input and output. Let's take an address of MW1 and then let's move it to MW2. Mm, So these are older tags, they might conflict. Let me delete all that. And let me reassign those tags so that I doesn't get conflict like we were getting in while using match instruction. So let me use over here MW1 and move it to MW5. So it's word data, that means having 2 bytes. So MW1 and MW2 will be occupied. Just in case I am keeping the difference of 5, and here I am keeping M0.0 as a condition. As it turns on, then my value move from MW1 to MW5. Also, I can use multiple output instruction as well, output addresses as well. I can add multiple output addresses like that. So let me just start my simulation and download the program. So now let's operate it. Let me change the display format first. Now let me modify it. Let me put some value over here by going to modify operand. Let me keep a value of 10 over here. So as you can see, it's moving. Let me keep 10 of decimal. Oh, let me edit that. Format as decimal. And now as you can see, 10 is moving over there. So I can use multiple addresses as well where I can move the same value. Let me put MW10. Let me download it. Download the changes. So now as you can see, values moved there as well. So whatever value is coming is being moved or copied into different multiple addresses. So let me take 20 and 20 is now being moved. So we will be using these move instructions at different places in our programs. Thank you. Now we are going to work on match instruction in DIA portal. We use match instruction to uh, we mostly use in analog processing or whether where we are doing some mathematical calculations like we are calculating production parameters or we are calculating some efficiencies, right? So there can be different applications and mostly we use SCL language, but right now we are going to perform on ladder logic. So that's the future case. I have DIA Bolter already open right now. On the right side, now I will use match instruction. There are different instructions you can see are available. So I'm going to explain some basic instructions as well as most used instructions, right? So as you can see over here, first I will use add instruction, which is quite common instruction, right? It is asking for two inputs. If I click on the yellow icon, I can add multiple inputs as well, right? So, and here I have to give one output as well. So I have three as input and MW1 as output. Let me select the data type as well. Let me take integer. So MW would be fine. Or there can be different data types, right? Which you can select over here. Let me select unsigned integer, which will always show positive values, right? So let me put over here MD1. I'm taking double word data type and I've assigned the tag name as add output. So it would add 2 plus 3 equal to 5 and move that value into MD1. Now let me use subtract. It would subtract two values, simple as that. Let me take MD1 as input and put a constant value over here like okay, let me take an address MD5 and put output in MD7. Let me assign the name as sub output. Let me take multiply as well and give two inputs to that. Let me give subtract output to multiplication input, multiply it by 5 and assign a different address. So let me correct it, unsigned double integer because I'm using double word addresses, right? So further, we can use increment decrement function as well. It increases or decreases the value, or we can use square root, square, and functions like that. Absolute function as well, modulus as well. Let me use a calculate function, which is a general mathematical function in which I can put a complete formula. Let me assign two inputs. So I can add multiple inputs as well. I can keep on adding them, right? And assign result output would go into MD12. Now this is the important part where I will added a complete formula. For example, input 1, which is IN1, having MD9 address, put this in bracket, multiply by IN2. Now let me use minus subtraction. Input 3, my plus input 4, and further let me use We can use for the instruction as well, right? So I can use I am using multiplication, addition, subtraction within the one formula. So for example, we are calculating machine efficiencies, or we are calculating speeds or production, we can use such formula. Let me now uh, go online. I am using simulation mode, turn on the monitoring and run. So let me change the display format to decimal, or you can use modify display format of complete network as decimal as well. So 2 plus 3 equal to 5. 5 minus 0 equal to 5. I can add value from over here as well. Let me go to modify operand. So let me give it 4, and 5 minus 4 would be 1. Let me reassign that. So let me check. I believe, yeah, it's not changing because there might be some sort of conflict with the addresses. So let me change it to 120. I should have kept more space because double data means there are 4 bytes of data. So I should have kept more space between addresses. So let me modify it to 2, and it should work, or 4. So it is working now. 5 minus 4 equal to 1. So 1 multiplied by 5 equal to 5 as well. So 5 output is going over here. So 5 into 5, 25. Let me use calculator to show you guys the result. So let me use 5 into 5, that would be 25. Then subtraction sign, and 3 plus 2, 5. So minus 5, and it is 20. So my output is showing 20 over here. I can further use or operate decimal points as well, like 5.0, 6.0, and use real data type instead of integer. So you have to promise me that you will operate rest of the instruction as well, just for practice. So in case in future you might have to use that. So I'm using an increment function right now, instruction right now. So let me use some addresses and assign a data type. Now let me use this function as well. Let me use a branch first. What's happening? Okay. So if I'm taking two inputs, and let's give memory address, So now let me download the program and check both these functions. So it is now returning the minimum value because 4 is smaller than 5. So I'm getting 4. If you use a max function, it would return the max value. Now we will see this increment option. So since input is on, my value is continuously increasing. So if I turn off this output, my increment stops. If I high, it is continuously increasing. I can use a pulse bit over here as well. So pulse, positive pulse or negative pulse, like that. So it wasn't increasing at a fast pace. Now let me use this. If I modify it, so at the end it's 999, and as I turn it on, the value increases by 1. So now, as you can see, value is incrementing by 1, or you can use decrement as well. We use increment decrement sometimes inside of counters as well. It gives us such values like that, and we can make these tracks retentive so that it should hold those values. So you can use other different functions as well from there. Thank you. So we worked on move instructions in previous exercise. Now we are going to work on convert instructions. So we have different instructions over here. So this one converts uh, different parameters into different data types. So for example, we have a data of a different data type that we convert it to real data type, or real data type to integer data type. So then we can use convert instruction. So for example, if I have data coming in floating point and wish to convert in integer, I can use that because we can't directly use a move value to convert integer data to floating data, right? So in convert, it is changing data time. In round, it is rounding off the number. Other than that, we have seal, floor, and trunk instructions. In seal, it generate the next high integer from floating point. In floor, it generate the next low integer from floating point, and in trunk, it just truncates the numerical value. And mostly we are using convert instruction or scale X and norm X instruction, which are used in analog processing, and we are going to work on it later on. So let's use convert instruction. So I was moving data from one address to another. If I show you in the tag table, so I have MD1. We can use swap, navigate through bottom options as well. So you can change data type from here as well. So this is real data type, which is a floating point data type. So it is MDs of 32-bit, 4 bytes data, right? As we cover different data types, real is 32 bits, which is MD, double word, MD or QD, and long real is 64 bits. If I show you in TIA portal, I have used MD, which is for real number. Now let me convert into MD5. It has automatically detected that it is a real data type, and I have to convert 32-bit into integer. Let me convert into unsigned double integer, which is 0 to positive values, right? So UDINT is its data type, and let me use empty 10 over here. So if I keep a wrong data type, it would display as red. It is still showing red, although I feel I have selected the right address. So I have taken MD50 at output since I had used these addresses with different data types already, so it was making a conflict. Now let me use MD10 again, and now it is not showing error. This is grayed out, so it's working well. Now if I keep it integer, it shows an error because integer size is less than the real size. So I have to match the 32-bit size of both. So now let me download the program and perform this operation. So if I use oops, so 1.7564, right? And it, sorry, it is converting it to the nearest integer value, that is 2. So since it is close to 2, it is showing 2 as an output. So you can use data types conversion like that, and uh, make sure to choose the right addresses. Everything regarding data types I had covered in the data type video earlier. Thank you. So now we are going to use program control operations or instructions. So you can see different instructions over here. Most commonly used instructions are jump and label. So this instruction would work when we are getting a high input. So, and the other one would work if the input incoming is low. So let me create a simple program to show you how we can use both of these instructions. So let me take a bit of M0.0 and an output coil. Let me name it Q0.0, right? Now we are going to create a second network recalling the same tag and operating one more output. Let me take M10.0 above. Let me make an intermittent logic by using momentary addresses. Sorry, internal bits or memory bits, right? So when I get this output bit on from M10.0, let me take M10.0 once more, and let me operate a different output, MQ0.1. So now I'm going to use jump instruction over here. Let me name it M0.1. Now, since I've used jump instruction, I have to give label as well. So both works together. I will give the label the same name that I'm giving jump output to. Yeah. So let me name it as output to. It is automatically detecting the label. So what happens is when M10.0 gets on, and from that I'll get Q0.0 operated as well and Q0.1 operated as well. But if M0.1 gets on, my jump instruction would be activated and this would skip the second network and directly jump to third network. So it would turn on Q0.1. Let me download this program and test it. Let me modify it to 1 so everything is working smoothly. Now let me operate this, modify this, and my network 2 has been skipped. So it being jumped to my output 2 label and turning on the second network. So this is how we can use jump and label instructions, and further we might have to avoid the instructions so that it delays the processing time if we include much of these instructions in the program. Thank you. Hello everyone, in this lesson we are going to work on analog programming. For analog programming with Siemens PLCs or analog processing, we use NormX and ScaleX functions or instructions. So what happens is, for now I'm using CPU 1211C DC and this article number. So in this exercise we are going to work on simulation, then onwards we are going to physical PLC as well. We have 0 to 10 volt DC voltage input channel. It converts 0 to 27648 value. Resolution is 10 bits and maximum withstand voltage of 35 volt DC. So what Normex done is we have defined the range, integer range 0 to 27648, which is its resolution. It converts into a real value of 0 to 1, which is called normalization process. This norm value goes into scale X and convert into the range we want. So for example, we are getting a voltage signal from temperature 0 to 10 volt DC. So it goes over here. Then it gets converted into a scaled value of 0 to 100 degrees centigrade. So we give this range in scale X. So it converts 0 to 27648 between 0 to 100. So for 12,000, it is showing 43 degrees centigrade temperature, right? So let's use that. Let me add a device. I'm using version 4 since we are going to work on simulation. Most S7-1200 PLCs have two analog inputs. It shows addresses as well. Q64, 65, 66, 67 because it is 2 bytes addresses here, right? So let me go to main OP. Let's take two instructions. Let me use NormX. You can select from the right side as well from conversion, right? So let me give 0227648 and let me give an output, any memory register. Let me take MD10 over here, and it is a real data type. Let me use scale X function now. Let me give a desired range. For example, I need 0 to 100 degrees centigrade, right? Which is the actual range which I need, which I am doing scaling from. So MD10. Over here, MD10 is the output coming from norm X. Let me give real, as I have taken over here. Let me convert into MD20. Let me rename all these tags. Let me rename it as scaled output. Now we can over here put input analog input register, or for simulation we can put any memory address as well. For now, I have input addresses of ID 64 to 67. So I can use these input addresses as well, or I can take a fixed value as well, just for simulation purpose, since right now I'm not using my hardware. So for example, let me open a calculator. Let me take its half, that is 13824. That means it should show 50 degrees centigrade. It's half, right? 0 is 0 degree and 27648 is 100 degrees centigrade. So let me simulate this. So as you can see on the scaled output, it is showing 50 degrees centigrade. So we have scaled the sensor value to 0 to 100 degrees centigrade of the desired range. So let me, for example, a signal of 8 volts. So this is my maximum range. So divide by 10, that means 1 volt equals to 2764.8. So if signal is of 4 volt or 8 volt, so value should be 22118. So 8 volt means 80 degrees centigrade should be the output. Let me download the changes, and you can see output is nearly 80. So if I have any memory address over here, we can use that as well. So for example, if I have a physical PLC and having these analog input addresses, so in these PLC we don't have output, we can use a memory output register as well. So right now we are doing input scaling. So let me use ID 64. Let me rename tag temperature sensor. So for changing its value, let's open the extended view of PLC SIM, so that I can change its values. In SIM table, in this project, I can add different values and simulate my tags. So if I click on load project tags, it would automatically load all the tags that are showing on tag table or taken in the program, right? So let me take it as decimal. Let us modify these values. Let's give this value and let's enable. For some reason my mouse cursor is not showing being moved. In any case, I have taken this moved this value, and if I go to my program right now, as you can see, it is showing 50-degree value. So I have put simulated value in ID64 like that. You would also see a slider at the bottom of PLC SIM, which you can use to change this value. So it is showing we are using in floating so that our resolution doesn't get wasted, right? Because it's 0.000 to 100.000. Further, we are going to work on analog PLC wiring. As you can see in the picture, we can like that attach any analog sensor. And other than that, we are going to perform exercise on factory IO as well, and use this instruction to operate automatic level tank example. Thank you. Hi everyone, this is Rana Mohammad Awais from Automation Play. In this tutorial, we are going to work on PLC PID programming in TIA portal. In previous exercise, we had used on-off control. As you can see, there were error between present value and start value. It was going on or off, right? So then input was not being maintained perfectly, right? So there's a condition that it can produce wear and tear in our system. So that is you can say sort of digital control as well. We were using scale norm extraction. Now then we were using on-off control with deadband. The advantage that we reduce some wear and tear, but still there was an error. Now we are going to use fully feedback control, which is PID logic, proportional integral derivative. We are using controller to control a process, and then we are getting a feedback from our sensor. Ultimately, PID output maintain output in a way to have zero error between process value and set point. So there should be zero set point. This is some diagram. Proportional is it would maintain stable condition. It would try to reach maintain present value with set point, but there will be steady state error. This steady state error will be removed by integral. It will eliminate that error, but there will be a problem of overshoot, and that overshoot would be counteracted by derivative. In proportional, we will be using gain. Let me show you that on TIA portal. Let me open version 14 template. You can use version 15 template for TIA portal version 15. For some reason, my laptop in which I have version 15 sometimes creates a problem on Windows 10, so I'm using version 14 on my other station which has Windows 7. Any case, let me open main OP. Let me switch this to ladder logic. Yep. Now for PID instruction, let me drag first. Before that, let me use norm X and scale X instruction that similarly that we had done in previous exercise as well. Let me open factory IO. Let me go to scene. We are going to use the same level control application. We are going to use this same application for PID. As you can see, level was ID30, set point is ID38, and SP and PV QD38, 30 and 42. So let me use norm X. And then norm X below there as well, and then scale X. I'm using two rungs because first would be for present value and then there would be scaling for set value as well. So for level sensor that I have to display on that meter, let me use 0 to 10.0. That is real data type, floating data type. This was ID 30. Let me use MD1 for output. So I have to scale it between 0 to 300 centimeter of range. Let me use MD1 over here. So for output, that was double integer, which is QD42. So that was double integer. Now level will be displayed in 0 to 300 centimeter of range. Now I have to do the same for set point. I will do it as real, so it turns blue. That was ID 38 for set point. Let me use MD10. Above there I had used MD1, and now I'm going to use MD10. I believe in previous exercise I had used same address, which was a mistake, but somehow it was working. Over here I will use 0 to 300 centimeter of range. Output would be QD38. Let me confirm that. Yep, QD38. So now I have values of present value and set point. Our error is set point minus present value. So let me use a subtract formula to calculate error as well, so that I can see it. Let me define it there as well in my tag table. My ID 30 was level sensor input, and my ID 38 was my set point that I will be setting on the panel from potentiometer. QD42 is my level display. And that was my set point display. You can name it as actual set point as well. Oops. Now I will go to main block. So now we will be displaying level and set point over there. Now we are going to operate it automatically, right? Now comes the interesting part. I will be using PID block. Let me add a new block, and for OB I will be using cyclic interrupt. Mostly we are working on program cycle, right? Now we are going to use cyclic interrupt. It allows you to start programs at periodic intervals. So at periodic intervals it will be scanning this block. So instead of being continuous scan like main OP, it would be periodically scanned at certain time, so that it does not burden PLC much, but however it is working in real time at the same time. So let me add this block. So in TIA portal, PID is always added to this block. Let me just put over here ID 30. That was my SP, and then my level. And let me go output to MD20, which was my error. Let me call it as error. Now I will go to cyclic interrupt. Now as you can see on the right bottom we have PID instruction. There are three different PIDs. I will be using compact PID. This is specifically for temperature. It is for specifically for valves, but the compact PID block can be used for, it is a general purpose PID which you can use for almost all applications. So it will create its own single instance data block to store data. I will click OK, and over here you can see the PID. So what would be the set point? It should be coming from my potentiometer, right? So it accepts in D word or real, and there are input in D word real, and this input underscore PR, it is in word. Our input is in real form, so we will give it over there, and output is in real form as well, so we would go do over there instead of output underscore PER, which is for word. So for set point we had SP, it's in real form, input was coming from level, and output would be going to I believe I did not take my output. My output would be fill valve, that is QD30, because I have to automatically operate that valve. It should this valve should turn on as per my level readings that is coming into ID30, right? So I have just taken these three tags in my PID, these three addresses. Now I will go to technology objects, where I will commission this PID and configure this PID. I will go make it automatic mode, so that it automatically turns out on and operate output. I will use input over here, input and normal output over here for my real input and output. I believe rest of the values remain the same for now. And now here is my PID parameters, which for now I will use manual entry. I'm going to use proportional and integral PI. Let me use 0.0 over here. I'm just using proportional gain as 1.0. Let me make other as 0 as well. Except for proportional gain and sampling time, I've made others as 0. Sampling time is something that how fast it converts the data coming into your PLC. Now let me go to cyclic interrupt. Let me turn on the simulation. It is going to take some time. Let me start it. And let me turn on the monitoring. So let me turn on the commissioning part, which have the real-time graph as well, where we can do tuning as well. So let me connect factory IO as well. I am just using level, set point, fill valve, and SP and PV, right? Discharge valve would be in force position. You can use PID for discharge as well. Let me start it. Get the set point to 137. Yeah, that would be fine. So now the output has already started coming. Let me take this side by side. If I start this, so you can see my graph values are now showing. So, and output is working as well. So if PID works smoothly, that means there would be some value in output. As you can see, my valve is operating right now. So you can see current set point and output as red. You can see both are going in parallel. So system is somewhat stable, but there is an error. Let me use this 100% zoom over there. Let me further drag it down. You can zoom in and out as well. So you can see my scaled output is trying to reach my set point. So it is right now stuck 116, 117. There is an error, and error would remain, right? Steady state error. But you can see the water is dripping right now. So it gives output which is proportional to the current error, right? So we can further increase its output by increasing its gain, that I will show you. Let me further zoom it. So there's no switching, frequent switching that we had observed in that analog process, right? But there's a water is dripping right now, but it is not completely off because it hasn't reached set point, but there is an error of 6 centimeter of level, right? So you can see 4.5 is set point and 4.42 is input, which apparently is not that much, but still there is an error. In PID we have to make sure there is no error. So let me just check one thing. Also you can see on the left side it says system is tuned. So let me give a condition by turning on discharge valve so that it should maintain the water level itself. So now as you can see, let's see how it reacts. So now as you can see, input is rapidly decreasing. Now I will go over here and let me increase the gain right now. Let me make it 10 and increase the gain. So higher the gain, quickly it would try to remove that error, right? So that is proportion. So normally we keep gain from between 10 to 30, right? So I've put it as 10. Now let's see. Let me just adjust it a bit. And as you can see on factory IO, it is 123, 137 is my set point. So there's still an error over here. Let me increase the gain again. Right now there is an steady state error. Let me go to commissioning again. And as you can see, system is trying to close the gap between set point and present value. But there's now still an error of 7 centimeter of level. You can upload updated parameters from over there as well. So if I have to calculate automatically these values, I can use tuning as well, but I was using manual entry, if you remember over there. Tuning is important first to adjust the parameters automatically. So in tuning, it would just increase and decrease the value, decrease and increase the parameters, right, itself. Now I will further increase the gain to reduce my error. I will make it 25. And let's go to commissioning again from the bottom. Let's update the parameters. So you can see there's still an steady state error right now of 6 centimeter. Let me further increase the gain to reduce this steady state error. Let me make it 30%. Now let's observe it. Let me zoom it a bit. Oops. Why I'm doing it wrong. Okay, let me try this again. That's better now. So as you can see, sorry, it is now, the output is now flickering, right? Earlier we had steady state error, but as you can see right now, so the output is now fluctuating. That is because we have now increased the gain too much. So if I was keeping it till 25, it was a steady state error. Now it is showing me the fluctuation. Let me further increase it. Let me upload this. So you can see the fluctuation has now increased. So there's an optimal limit of proportional gain that we have to keep. It is true for all PID controllers. So you can see fill valve is fluctuating right now. So earlier we had steady state error when we had gained 10 to 20%, it's in percentage, and now we have oscillations or fluctuations when we are increasing gain. So if we use proportional, we still have some kind of steady state error. So for remove that, we are going to use integral. Now let me go to configuration. Let me keep the optimal value for proportional gain 20%. Now let me use integral. Let's start with 1 second. It's in time, its unit is time, so I'm starting it with 1 second. We have to keep it as low as possible integral, because if we keep a higher value, system would get unstable real quick. Let me remove these differences in lower level component. Right now we are doing simulation, right? So it works slightly differently, or it can work as compared to your physical hardware. There might be some variations, but all these configurations should be the same. So now I have put integral. Let me upload the parameters. Let's check out the system now. So the system is now responding rapidly. Let me increase the time. Okay, normally we keep it low when we are working on physical process, but right now in simulations it only works when I increase the integral time on factory IO. So it totally depends upon your system and how much reliable or error free your system is. So you can see the response is now stable. I believe it should further remove the error. It's on 136. It is reducing right now, and you can see over there as well. So it's 0.02 difference of 0.02, right? It is still trying to reach the set point. So what integral does is it's keep adding the gain as quickly as possible to reach the desired set point. So gain was in proportional, and the time it takes to increase the gain, it's in integral. So as you can see, we have finally reached the set point by using proportional and integral, our PI controller. So I hope you all guys practice it this way. It's a really good exercise. As you can see, system is running smoothly. As you can see, there was a steady state error, then we had fluctuations or oscillations. Then finally we are, you can see after putting integral value, you can see this present value has reached a set point, or measure value has reached a set point. So PI controller is often called the match made in heaven, because P plus I stabilizes the systems really well. Sometimes in most applications we only use P plus I, but if we have an overshoot, we can then use derivative as well. So if there's an overshoot, you can if there's a overshoot, that means value is going up and down too quickly, you can use derivative value as well. Right here it would be in time unit as well, in second, but for now I don't need it, so my system is already stable right now. So this is how you can practice PID with TIA portal, and I believe by using the commissioning method you can easily observe as well, and you can simulate further. You can use PID, one more PID loop on its output valve as well, on discharge valve as well. Or you can design multiple tanks with multiple PID loops in TIA portal. You can create your own exercise as well. Thank you. So thank you so much for completing this workshop and session on my YouTube channel. I really hope you found it useful and you can implement it in real world as well. I really hope you found it useful and it helps you to start in automation world or to start with Siemens PIA portal. You can check the complete course and specialization links in the description as well. You can join at Automation Play. So thank you again. Take care. Bye.